Good morning, everybody. I hope everybody had good rest and we are ready to start our new day. Today we have the second day of the conference, and just to remind you what is in our agenda today, we have in the morning we have the keynote by Gabriele. Just try to learn her name. Good, Cicorli. Then after lunch break, we are going to have panel discussion. And then in the evening, we are going to have the session. We are going after the keynote in the break, we are going to have a session on machine learning and security, then the lunch break, then the panel, then the break, and session number 4 on mobile security. And yeah, so I'm giving now the stage to Yongdae. He's going to chair this session.
Yeah. All right, I'm Yongdae Kim, and I missed yesterday's introduction because I am flying from Korea, and it took like 24 hours for me to come here. And I'm one of the other Foreign Committee co-chair with Daniela, Alexandra. And today I will introduce keynote speaker, Gabriela. So she's going to talk about security and reliability for critical infrastructure in smart manufacturing. And so she's an associate professor in the Department of ECE at the UT San Antonio, here local. And she's also vice president for securing automation and secure manufacturing architecture for Saimano. And her expertise has been in anomaly detection, distributed alert correlation, network and application level security, cyber physical systems, security and distributed system. Actually, her expertise is actually very similar to mine. And so actually, I was talking to her in the morning, and she worked like 9 years in SRI. And I was actually wondering why she moves to academia from nice research environment at SRI. It seems that she likes working with the students with the freedom. And I think now she's working on very critical problem. And I mean, in the morning we discuss about some of the critical problems and in the critical infrastructure and how they are managing the security. And I think it would be very, very interesting talk. And so let's welcome Gabriela to give a talk about security and reliability of the critical infrastructure.
Thank you so much. For everyone who is close by, I'm going to remove my mask, but put your mask on because my daughter was exposed, so let's just be safe. I just got an email that she was exposed on Friday, so there is a potential for me to be a ticking bomb, just so you know. Okay, so thank you everyone for being here. I would say just a few words about Saimeni. So Saimeni is a secure manufacturing institute. It's led by UTSA, and it's a large institute with a lot of different organizations from industry, from universities, and also from national labs. So this is I'm very excited of being a part of Saimeni, and of course I'm very excited for being a part of the faculty at UTSA. Okay, so why do I talk about connected? Why do I say that everything is connected? Actually, if you look around, we are all connected. We all have our phones. Everything is really connected. Wherever we go, whatever systems we are talking about, whatever manufacturing system, whatever your homes are highly connected. So I've done work in different research areas, and today I just want to highlight interesting aspects that we discovered with our work, but also interesting aspects that would be interesting to consider moving forward for all our research, especially in the community here. So, for example, we are talking about cellular network, right? There are so many systems that rely on cellular networks. There are IoT systems, there are the car industry, right? Everything is moving towards connectivity, and they all rely on cellular networks. So then the reliability of cellular networks becomes key. And then we have all the different IoT systems for which we want security. But we want security and we want privacy at the same time. We want everything. And there are sometimes conflicting goals that we want to have for such systems, right? And when I'm talking about IoT, I'm talking about smart cities, smart cars, smart everything. We are moving towards an even more connected world. And we have so many interconnections between individual infrastructure, but across infrastructures. Again, cellular networks are supporting the IoT. Then we have IoBT. This is another area that I explored a few years back. That's a different kind of environment. Even if it's an Internet of Field, it's an Internet of Battlefield. So you have a particular type of interaction, and you have there is a different trust model when we talk about IoBT. So there are very interesting challenges there about trustworthiness. And then secure manufacturing. We are all, if you look around again, everybody has something that has been manufactured to some extent, and everybody has to rely and trust all the things that have been manufactured. So there is a very interesting area of building secure manufacturing systems on which we can trust the final product. And I'm going to talk a little bit about that towards the end of the talk. But again, I just want to highlight that the fact that all the systems are connected, that's the key thing that leads to security issues. And critical infrastructure is becoming more and more a target of attack. For example, in DHS in 2020, they were saying that there are a lot of spear phishing links to obtain initial access to IT networks and then entering the OT networks, the other side, the operational sides. Then critical infrastructure again relies and can suffer degradations in performance, and then implicitly there is a cascading effect in other infrastructures that rely on them. And then let's not forget that every time we talk about critical infrastructure, we talk about cyber-physical systems. So it's not only, we cannot treat them in isolation. There is always an impact in the physical world that we have to keep in mind. So having all of these and reminding ourselves the connectivity, I'm going to highlight a few areas that I explored when talking about IoT security. So again, I explored the angles of connectivity. How can we identify devices and monitoring devices for anomaly detection? But again, this is an interesting aspect because there is the privacy angle as well. You want to monitor device, you want to know what's happening with a device in an IoT network, but at the same time, you can expose privacy, also the privacy of the person who might wear a particular IoT device. So then how can we, I also looked at ways in which we can model the cyber-physical channels and attack paths that can happen within an IoT device, an IoT network. So imagine that you can actually, in a formal way, you can define how devices interact with each other. And by using verification techniques, you can also expose the unwanted channels of communication between devices. So that's another angle that is relevant, especially when we talk about cyber-physical systems. And then causality, like everyone wants to understand how systems really work and how systems influence each other. And we talk a lot about correlations, but correlations are not that relevant in reality. What we really want is causality relationships between large IoT systems and systems in general, right? Even when we talk about enterprise networks, we have attacks in enterprise network, we want to show the causality relationships of an attack that is spreading throughout an enterprise network. And then I've done work where I was looking at the types of relationships in terms of commands over industrial control systems communication and how those can expose, again, malicious commands and data sequences in those communications. So all of this work and all of the work where we are looking at interactions is actually, again, coming together towards this connectivity of IoT systems. And we saw that the connectivity actually opened up a lot of interesting doors for attackers. There have been, throughout the years, so many attacks, like from the ultrasound commands for Siri, Alexa, and Google, to the camera, to the toys that kids had to suffer through, and to the industrial pumps attack, where bubbles could actually damage the physical part of the pumps. So a lot of types of attacks. Sometimes not all of them going on connectivity. For example, the bubbles, the evil bubbles, is not necessarily a connectivity, but in the end, the attacker has to have some access and some connectivity to a system. In some cases, physical. So I will just highlight some of the results in our work. So we've done. We wanted, with this work in particular, we wanted to see how can we determine if IoT devices have been exploited. How can we see that on different types of communication protocols, on Bluetooth, on Zigbee, or on Wi-Fi, and how can we determine that, and can we do it in a generalizable way? So this work was quite simple in a way and cute. So we just looked at the types of the network traffic on all these three different communication channels: Zigbee, Bluetooth, and Wi-Fi. And we wanted to make sure that devices in an IoT setting, we had an IoT setting that resembles the home environment, and we wanted to make sure that devices are not changing their behavior, because that could mean that there is an attack. So the goal was to detect anomalies by observing clusters, and also by also considering where the devices are located. So by measuring this type of behaviors in the IoT networks, we were able to identify classes of devices. We were able to identify, for example, that we have multiple echoes. Even if they were different generations, they were behaving similarly. We have multiple sensors. Even if they were different generations, again, they were behaving similarly. And we also considered the physical properties of the devices by looking at the RSSI signal to understand the physical location of these devices. So we have the classes, but to be able to identify instances of those classes, we were looking at physical location. So we evaluated our work on 21 devices, and on a data set that while we were working on this together with the interns, there was a new data set shared with the community in IEEE SMP. So we wanted to show that our method is general enough, and applied the same techniques on that data set. And then we wanted to show that we are able to do anomaly detection, and we tried different approaches there. So just quickly, I will give you an idea of how our system looked like. So again, we were sniffing Zigbee, tapping into Android through Bluetooth, and we were also collecting the Wi-Fi traffic. And we extracted RSSI features with the direction estimation. And then we wanted to to have the ability to identify the different types of devices that we had in the network. Then by using the location, we were able to say, hey, did something change in this network? Are my devices starting to behave differently? So that was the anomaly detection part. And then we had a way of displaying all that information. So in terms of the device type authentication, we looked at simple features. We looked at interpacket time, payload length, packet length, payload entropy, and packet entropy. And I know that these are, and then all the statistical values for those. And I know that these are simple, features, but they were quite relevant when we talk about simple sensors and simple devices that we have in IoT, smart buildings, smart homes, and so forth. And by doing that, again, we identify the different types of devices, and then we also looked at the device direction identification to understand how and where those devices in the certain classes are located in a system. And again, by using the RSSI signal, this didn't require sophisticated techniques or new types of hardware to understand better the location, and we were able to identify the location of the devices. And in terms of the anomaly detection, again, all these devices were clustered. We had different clusters, different centroids for each individual device, and we were able to determine when a device would change its behavior. So let's say that our evaluation wanted to answer the following. Is our clustering technique able to cluster different devices? Is it generalizable? Can we apply it to other data sets? Can we detect the direction of where the devices are located in a physical space? And can we do anomaly detection on all of these? So we didn't need too much traffic actually to extract these behaviors. So for example, for 7 hours, we collected Wi-Fi traffic, and we were able to achieve very high accuracy for clustering the different classes of devices that we had in our network. And similarly, we applied the same technique for Zigbee and Bluetooth. And all of these were the classes that we discovered, and these are, for example, these are the clustering performance for all the different types of devices for the iPhone, homemade smart plug, and so forth. So these are the performance metrics that we discovered for all of them. And again, we didn't need too much traffic data because all these devices have a pretty simplistic behavior in a way. And then we followed with the second data set from IEEE SMP paper, and we were able to achieve similar numbers also for their set of devices. So this is just just shows us that even with simplistic features, we can actually determine very easily what's happening in a network, in an IoT network, with respect to sensors and simple actuators. And then we looked again at we evaluated the device direction identification, and we were able to actually test our approach in two different setups. One in our setup in the office, and we actually set up a second similar test bed to see if our approach holds, and we had a very good results in that respect as well. So we had accuracy of 95 and 85 for 4 directions. So we are not, the method is not as good as at finding 8 directions. So the accuracy was decreasing because the RSSI signal is not as strong, and it doesn't give us enough information when we looked at 8 directions, but it was pretty good for 4 directions. And then we follow through with different anomaly detection scenarios where first we just use different protocols, we use the cryptocurrency miner, so these are more obvious types of anomalies, but we also had an IRC bot on some devices and we were able to detect those. And again, these were the different clustering, the different clusters for the different types of devices. Every time one of these attacks would show up, the clusters would change their shape and indicate that there was an anomaly. So this was, again, this was a paper that got the Best Paper Award in the IoT conference in 2020. But I think that its value is also to show that sometimes simple features can give us a good indication of what's happening within a network and for certain types of devices. This will not work for much more complex types of interactions. It would not work in a enterprise network scenario where you have much more variability and the behaviors are much more complex. So again, looking at all these connections, looking at all these connectivities and looking at how devices interact with each other enable us to identify these types of sensors or all sorts of IoT devices, and also allowed us to do direction estimation and know where they are placed in a particular physical space. But this comes with a drawback on privacy, right? What if we are talking about devices that are attached to humans and we don't want to reveal that information? So we always have to have this type of trade-offs where, yes, we want a network where everything is monitored, and we want to know for sure that our devices are secure, but at the same time, we don't want to leak anything about the privacy of the users in that environment. So that's an angle that we didn't consider in this work, but I think it's also relevant to see to what extent can we say which devices are actually revealing anything about the humans in the area. So that would be a nice extension to it. Then in terms of cellular networks, I've done some work for 4 years. We collaborated with Nokia Research, and we had a lot of different angles in analyzing cellular networks from a reliability perspective. So we were looking at the health of cellular networks. How can we determine if cells in particular have abnormal behavior? How can we not only detect but also diagnose a particular network? How can we, when changes are made into a cellular network, we were working with LTE. I want to emphasize that this is older work. We were focusing on LTE, not 5G. We were also looking at ways in which particular changes that are made across the whole cellular network would have a negative impact. That's something very relevant. And if we think about it, that would be even more relevant in the setting of digital twins. So ideally, you don't want to push a network change. Ideally, you want to test it ahead of time. So our techniques should have been even more let's say, robust if we could do them without assuming that changes have been made to the network and then observing if the network is going into a strange state. And then one other interesting topic that we were also looking into is whenever we set up a new system, we don't have a behavior of that system. We don't know how the system should interact. So if you have a new network, how can you transfer the knowledge that you have from other networks to these new networks so that you understand if the network is behaving normally. So that was another angle that we were looking at. And again, it's a matter of understanding these connectivities between between cells and how certain areas might influence the overall behavior of, and I'm talking about physical, geographical areas, might be influenced by weather-related events and so forth. So this work again, I want to highlight the fact that we are moving towards the private cellular networks. We are moving towards the smart airports. We are moving towards the 4G cellular networks on the moon. So having the ability to say something about reliability of these networks and also security of these networks is key in so many new scenarios nowadays. And then the supply chain is another beast, which I'm going to talk about a little bit later. So just to highlight a few ideas that we had throughout this work, and again, this was done a few years back, but we were operating in we didn't have any labels, so non-label setup. We had access to these key performance indicators for every cell in a particular network, and we were trying to figure out, is this cell healthy or not? So again, all these systems are highly dynamic. Operations change over time. There are different parameters that are changed. There are different configurations that are changed, and so forth. The users also have an impact. The volume of users that are attached to certain cells is also has an impact. So we had to come up with this was the first attempt to analyze that data, and we came up with an approach that was trying to characterize every cell based on these key performance indicators. We tried different models, and we continuously updated these KPI models just because, again, there is this dynamic aspect to the networks. And we employed an ensemble method approach that was giving us the ability to understand what's the performance of all the different models in our ensemble, but also we had some extra information. We have these configuration management changes, so we had a way of understanding when something was supposed to happen in the system. We didn't have necessarily labels, but we had this context information, the configuration management information. So the first experiments were only on 70 cells that we had access to, 12 KPIs, and again, no ground truth data. We worked with subject matter experts to understand how we could label the data so that we can verify our results. We used all this contextual information that I was talking about to understand when changes happen in the models and how to age out models and so forth. And we were able to reach some very, very good results overall in terms of the average detection rate and the false positive rate. So these were the different types of univariate and multivariate approaches that we took. And again, we had decent results. And we continued the work, and we looked into this idea of zone coordination or verification. So this idea of making a change throughout the whole network, see if the network changes behavior or not. Again, all of these are related to this concept of connectivity, because all these cells are working together to provide a particular service, and they are configured in such a way. So with this zone verification idea, we wanted to do not only detection, but also diagnosis. So we were inspired by one concept that a lot of people are using in NLP, topic modeling. And we wanted to see what are the topics in a particular cellular network. What kind of states do you have normally in a network. So we were able to discover these topics or states in cellular networks with respect to these key performance indicators. So the network can have will have a mixture of key performance indicator behaviors in all these different states of that we were discovering. And we had a way of interpreting that. What was nice, we didn't have labels, but you can actually interpret, and we had a way of interpreting the states based on the actual characteristics of the key performance indicators, because we had drop call rate. So we know that a very good drop call rate means that you don't have drop call rate, right? So we had a way of automatically inferring if some KPI state is bad or good. And by doing that, in the detection mode, by discovering all these different topics, all these different states in which the network was, and having a way of interpreting those states, we were able to also say whenever the network would be in a bad or good state. And more than that, we wanted the diagnosis. We wanted to understand why all of that was happening. So we used the Markov logic networks, which are very easy to express as first order logic. So you express certain rules, and then you get the most likely explanation for a particular state. So we did that. We combined topic modeling and MLNs to understand how certain states of a network were how to diagnose them. So when I'm talking about diagnosis, we wanted to understand again if certain configuration management in the network were having a bad influence. So if we could see that there was a relationship between the configuration management changes and the state of the network becoming bad, then we knew that those configuration management changes would be the reason for the degradation of the network. So we were, again, we had data for 3 months from 9,000 cells. This time the data set was much larger. Of course, whenever you have real data, you have missing data points, so we had to make up for those. Again, no ground truth, but we had the information on the configuration management. We had the information, and we had a way of interpreting the different key performance indicators because they are self-descriptive in a way. Okay, so once we analyzed our network with 9,000 cells, we discovered 32 topics, 15 normal and 17 abnormal. So we could distinguish between all of these different states. And this is an example of an abnormal state where most of the cells exhibit a call success rate that is not that great. It's actually a degrading call success rate. And in different phases of the communication, those are different KPIs that are defining different phases of the communication. So by doing that, then we were able to identify what cells are influenced by certain configuration management changes. And actually, a configuration management change is actually a change in the angle of the cell. If you change the angle of the cell too much, then you can change the key performance. People might not be able to access the cell if they are in between cells and you change the angle and they don't have coverage for that particular area. So this was a very interesting result that actually show us that we have a way of identifying and diagnosing system even when we don't have labels, and that's the key thing. And then one other thing. So this is another way of showing the results on the angle. We also looked at weather and see if the weather in the area where the cells were located had also an impact with respect to the performance of the cells, and we found similar we found certain events in the weather that actually led to degradation in performance. So all of this was quite interesting work. And again, we were relying on information from the cellular networks to understand its performance. But think about attacks also. If we have attacks and we have this type of key performance indicators, we can also detect in the same way potential attacks on cellular networks in a similar way. So this was just this was work that was exposing problems due to configuration changes or weather-related changes, but in the same way we could detect attacks. Okay, so let's see. What about secure manufacturing? So I've been showing all these different angles on IoT devices and on cellular networks. But now we are talking about secure manufacturing. We are talking about the supply chains. We are tackling a completely different new era, because the supply chains nowadays are hard to be tracked. We don't have instrumentation. We are moving towards digitization of manufacturing systems. But can you tell me where all the chips on your phone came from, and if they were tested, if you have any way of really trusting your phone? Probably not. None of us can, right? So that's one of the keys that we are looking into for secure manufacturing systems. But I would say that there is now a good time to think about formal design specifications when we are building new types of systems. So even for IoT devices, even for 5G, we can look in ways in which we can formally define systems and do that at the design time when it's the cheapest to understand and remove any potential attacks or any potential reliability issues. Both of them are equally important. And then, again, going back to the phone and to the fact that none of us knows exactly what's happening in our phones in reality, in terms of the hardware that we have, having a way of extracting provenance information and being able to say, to see all the information about our phones and have some guarantees with respect to how a particular part is manufactured is key. And then with the pandemic, we also saw that we need to be prepared for pandemic adaptive supply chains, right? Everyone noticed that, oh, and now we have other types of supply chain issues as well. Yeah, the baby formula is the newest one on the list. So there are so many different ways in which we can use certain lessons that we've learned throughout the years to actually be able to have processes that are verified and processes that are monitored. And funny enough, biopharma systems are targeted more and more in terms of attacks, and they lack a lot of the security mechanisms, and they lack actually the ability to collect provenance information. Even if we know that every vaccine that we all took had a particular batch, so we can go to the batch, we can go to information like that. But when we talk in general about biopharma, we lack the security mechanisms, and biopharma brings another angle that is very strange, the fact that we have a stochastic nature of the living system. So these are different challenges that we don't necessarily have for other types of manufacturing systems. But again, this provenance information is missing, and is missing across multiple manufacturing areas. So we have a paper that was just accepted at IEEE S&P magazine, where we talk about this concept of a pandemic adaptive biomanufacturing. And the pandemic aspect is obvious at this point after 2 years in the pandemic. But then even if we have capabilities of building automated secure manufacturing systems where you can adapt and accommodate new types of products, you also have to allow users, you still have humans, you have to allow accessible and usable usability of the authorized users. And then we have to think about all these aspects of resilient and security manufacturing systems. And again, connectivity is the key part, because we want to make sure that we build systems for which we have strong security guarantees. And last but not least, of course, there is an economical angle. We always have to have systems that are relatively cheap, so that small and medium-sized manufacturers can also employ. So let's think a little bit more about the manufacturing. What did we learn from this pandemic? We learned that it's never good to have products and to have stockpile of fully flashed products. We saw that with the ventilators, we saw that with a lot of different areas. So ideally, when we build the future types of supply chains, we want to make sure that we have raw materials in stockpiles, so that it's easy to put together and to orchestrate infrastructures that can easily allow us to build products in a very pandemic efficient way. So just imagine the following. I think in around 50,000 companies have their supply chain, the tier 1 supply chain, coming from the Wuhan area. And then the second level supply chain, actually there are 5 million companies that are the second tier, have the second tier supply chains coming from the same area. So this is the problem, right? If a particular geographical area has a particular issue, we cannot rely on those. We have to diversify the supply chain. And then digital inventory is another thing that is very relevant when we talk about supply chain. So we have to have the ability to have the designs, to have everything accessible, right? And everything secured, and everything ready to be shared with the parties that could start producing the different parts. So we have to have digital inventory designs, data, and templates, so that we can easily scale up a manufacturing system. So again, this is not an easy task, and it requires a lot of interactions and connections between the different factories, the different stockpiles, and the critical facilities in which all these products would need to be put together. So imagine how complex these networks should have to be, right? Imagine how what types of communication do we have to have in place? How quickly we need to act in such scenarios. The technical expertise is another thing that needs to be handy. And then let's switch to the digital ecosystem. So in order to be able to achieve these pandemic effective capabilities, we need to have digitization, and we need to have techniques in which we can, again, collect all the information. We have this concept inside Symany of a digital passport. So imagine that for everything that happens within the manufacturing process, we capture the state of the machines that were operating and were producing different parts. We have hardware and software traceability. We have all the different characteristics of the products that are generated in the manufacturing process. But we are relying on sensors, like we were talking about earlier, right? To collect all this information, we have to have sensors that we trust. And that's a very important part, and we need to be able to have ways in which we can remove certain security issues at the design time, but also have monitoring capabilities at the operational time, so that we can say something about the health of those sensors. And digital twin can also be very, very important here. If we have the ability to build digital twins for not only manufacturing systems, but IoT systems in general, then again, we know when changes happen. We were talking about Tesla earlier, right? I wonder if they have anything like that behind the scenes, if they have the concept of a digital twin before they push any of their changes. Do they have a way of verifying that they are not going to impact negatively the performance of the cars? So all of these are needed. Otherwise, we cannot have reliability in systems like that. And if we can prevent, I think prevention has to be our future. How can we prevent? Can we use formalism? Can we use prediction? Can we use prediction mechanisms? Can we use these digital twins to tell us if something will go wrong? All of these are key for the future because they give us the ability to prevent. If we detect, it's a little bit too late unless we have other mechanisms that constrain the effects of attacks, instead of having cascading effects. Maybe you can constrain the effects, and you detect it within a particular smaller set of your system, and then you have resilient systems that can address the failures. But anyhow, I think we have to think more in terms of prevention. And we know whenever these systems are built, we know there is a particular intent of the systems. We can model the intent. We can model even we were talking also earlier, we can model even the control systems. And we can understand when they start to exceed the safety envelope, let's say. So there are all of these techniques. I think as a community, we have to explore them and come up with stronger guarantees in terms of security. So I think, where does the future take us? There is no one infrastructure. I think there are only, we cannot talk about one infrastructure. All of them are connected. If we are connected via the internet, we are connected somehow across different infrastructures. And we need security across all of them in a way, or we need a way of understanding these interconnections between the connected infrastructures. Ideally, we should have security guarantees from design, implementation, and deployment. And then there is this transparency and explainability, right? We want transparent systems. We want to understand what's happening in the system. We want to explain what's happening in the system. We want to explain when a particular attack, how that happened. We need these properties in our systems. But then privacy and transparency need to also coexist. And I think that's a challenge because sometimes, again, this is probably harder to achieve in some cases. If you want full transparency, how do you do that when you have privacy constraints? So yes, we have to explore privacy preserving mechanisms, and we have to have them at a scale that is needed for very large systems. So I think these are the future challenges that we are all going to face, and it would be nice to have some answers in the next years. Okay, I'll stop here, and I would love to have more discussions. Thank you.
Any question? Be good if you identify yourself.
Edward Knightley from Rice University. Thank you for the very interesting presentation. I have a question for you about the first part, anomaly detection, and especially, well, maybe both Internet of Things and cellular. And what are your thoughts on how we differentiate maybe from flash crowds or other events that would change kind of the mean operating point? Do you call all those things anomalies, or are you trying to differentiate from those other rapid changes?
That's an excellent question. Thank you. That is always an interesting question. And I think having extra context information can give us more abilities to distinguish between the different changes. For example, when we talk about industrial control systems, there are different modes of operation. So we need to be aware of those, and we need to be aware of a system going into a maintenance state, right, or into a different state. Yes, I think just doing anomaly detection blindly will not take us to where we need to be. I think we need to try to understand this extra context for all the systems so that we understand better what, again, causality. I've been mentioning causality. We need to understand the causality of the anomalies to be able to have a stronger system.
Okay, thank you.
Thank you.
I have a quick question about that. So was the data from the single tackle, or was from multiple?
It was from one. So it was one network. Yes, that would have been nice. I later on in other papers, I had a lot of papers there. We had data from different networks in different geographical areas. And there were some similarities between them, but you have a good point. If it's from the same...
Because, so this is Mike just comment. We actually had a measurement data from 28 tackles globally. It was our paper in 2018, something like that. And basically, we compare the control plane operations.
Mm-hmm.
And for example, like US AT&T is the worst in terms of performance.
Okay.
And when you go to Korea, I mean, your core setup time in the US was like 3 seconds. Korea was like 0.5. I mean, so the quality of the cellular network is so different.
Across.
I'm not sure whether those high-level KPI.
I think I mean they are important within the same operator. They are important for the same operator. So I guess you have to have a different interpretation for other operators.
Another point we also made in the paper is that because the tackles never compare against others. They just worry about their measurement. So they have a tunnel view about their system. And usually you use just a one tackle. So you don't know how good yours compared to others because you cannot compare. And I think this is exactly the problem of the cellular, manufacturers. And they know that actually they should have compared against, different tackles. Then actually it may show some cases good data, some cases bad data.
Yeah. Well, my collaborators were willing to publish all this data, and we were talking about it in different events. But I can see if there is no standard way of measuring the performance, it's a little bit difficult to have this comparison across operators. But I have to tell you that when we were playing with this idea of transferring knowledge from one network to a newly set up network, that definitely worked for the same operator. Probably it wouldn't have worked across different operators, but for sure you could actually transfer information from a given network for which we had all these models. And when we tried the same models in a newly set up network, they worked for the same operator.
Thank you for this amazing presentation.
Just identify yourself.
So my question is related to classifying the IoT devices that you have mentioned. So if you could expand it a bit more, because did you classify it based on the functionalities of the devices or the types of data that has been collected?
I was mentioning that the features were they were network features. Just a second. So we were just looking at those features to be able to identify the different classes. And when we, 1 second, here, interpacket time, so very simplistic network-based features were actually giving us a lot of information about the different classes of sensors. And I guess they are also very vendor specific in a way, because they are very vendor specific. They use the same stacks and whatever. Yeah. So then you can extract these behaviors. But that also tells us that we can use these simple statistics to figure out when something goes wrong in these networks, and why don't we do it? Yeah.
Thank you.
Follow on to that, and then I have another question. But we have a paper at WiSec called Home Station a couple years ago, where we go individual behaviors within devices, and exactly what you said, like D-Link devices look like D-Link devices.
Yeah.
And so within then you can differentiate, but the stacks are so similar. So at the end, you were talking about kind of a lot of motivation for provenance, right? When I think about provenance, I think about more of the detection side, kind of figuring out what happened, what could have happened. But then you kind of had this call for prevention, right? And I think there's actually an opportunity for these to kind of come together in a way. And I think I was following your train of thought there, and I was wondering if you could expand on that a little bit.
Yeah. So prevention allows us to build systems. Right? Okay. If I start again from the formalism, formalism allows us to build systems which are cleanly defined. You have the interfaces between the different components that are talking to each other. You can change the abstraction layer at which you want to define security properties and so forth, right? If we are talking about the micro or the macro levels of this high infrastructure. That's one thing. Then we have prevention, but then we also need, with the prevention, with the formalism at the beginning, we can reduce certain classes of attacks. But we all know that that will not mean that we reduce everything. However, if we do it early on, it's much more cost effective. Then later on, we also have to have monitoring capabilities that enable us to understand even more if the systems are functioning correctly or not. But we have to have ways, whenever we do this detection, right, we have to have ways in which we can either constrain the effects of what's happening in the system of the attack, or we have to have a way of predicting. So not getting to the detection, but actually preventing for the full attack to be finalized. So provenance can give us that information. For example, for a manufacturing system, we can look at the geometry of the part that is being produced. And when you see that the geometry is starting to deviate from the normal, from the golden standard that you can have for a part, then you know that something is happening in the system. So you will not take that part and move it to the next level in the supply chain and propagate the an attack or a fault throughout the supply chain. So you can stop it and you can prevent it before it gets too late, before it gets into a plane or who knows where, right?
And I guess one of the big challenges with provenance is knowing what do you want to record, right? What are the features that you eventually want to write policies about on that, and how do we discover those in the first place?
So I think those are discovered together with SMEs and people who are working very closely to different machines, and they have already a sense for the different types of sensors that are needed. And in our discussions with a lot of industry partners, there is no formal, definition of what those are. And I think it's important to discover them. And capture that information. But we all know about SBOM, right? SBOM is now a very is a work is more than in progress. It's been evolving a lot in the past years. And I think there we immediately see the value of being able to track down the software that goes across a supply chain and so forth. The same kind of idea, we have to do it for hardware, right? We need to understand what's happening with respect to the hardware that is used in the different manufacturing machines. And the same idea has to go with respect to the context in which a part has been built, because the context tells you the health of a part as well, right? What happened on the machine? What is the geometry? What is the energy consumption? We look at energy from two perspectives. Energy is important because you want to be energy efficient when you do manufacturing, but also energy can give us some very interesting indications in terms of security. So if you see that your energy patterns change, there could be a potential. I mean, that can be a.
So it's interesting that you kind of moved to the SBOM there, because conversations I hear about SBOM is, well, it's nice, but what is it really giving us? It's not actually giving us the information we want about the vulnerability state. It's just a kind of, we have to do this sort of thing, which kind of gets at that root of what is the information we actually want to get at in these different domains, right? And so SBOMs really want to get the vulnerability information, which is right there. In this space with the hardware, what is it that it just sort of goes back to the question of what do we actually want to be recording in the provenance?
Okay, so so specifically for manufacturing, you want to understand if the part that you got actually matches the design. That's what you want, right? You have a design and you want to make sure that at the end of the manufacturing process, you have a match between the design and the part. And every manufacturing sector will have different types of machines involved and will have different ways in which they can qualify what is the quality of a part. If we're talking about a CNC machine, again, geometry is key, because you have the design and you have to make sure that the geometry of the part that comes out matches the design in terms of the geometry, and not only the geometry, also the material characteristics as well. So there are, right, you have to have the correct mass distribution, for example, and so forth. There are so many interesting aspects to look into.
Yeah, so I'm not
Yes.
that's the labor of it. Yeah, anyway.
Yes, thank you.
I mean, in terms of testing, I mean, because I work on cellular, I know about cellular testing. And so when you look at the cellular standard, there is a conformance test suite that mostly checks good messages.
Yeah.
I mean, good messages are handled correctly. So you may be able to test whether good messages are handled correctly, but I think one thing we found is that because the specification does not deal with the negative cases,
Exactly.
like violating cases, can you actually systematically build like a good set of violating cases that if those violating cases are handled correctly, like exception handling is done correctly, I mean, there is no such standard.
No.
And that's why there are a lot of bugs. I mean, they are not handling the exceptions correctly. And so, and I think in terms of for example, manufacturing machines, I don't think there is a good design. Right? The design should have actually no bugs. And then finding bug-free design itself is difficult. Once you have a design, then you need to have a testing.
True.
Right? And if you do not have good design, I mean, probably they don't have any formal verification for the design. And then there's no testing. So you cannot guarantee any like a correctness or anything. Right?
There are testing even now, but what if from the design to the actual hitting the machine, somebody interfered and suddenly the design was correct, but somebody changed the G code that is running on the CNC machine. somewhere in the middle. And then on the machine, you have an incorrect G code. The part that is manufactured will not match the design at that point. So there are all these different points on the manufacturing pipeline that needs to be verified so that you know that the integrity of the design is maintained, but that integrity changes its shape. It starts from a file of a design, but then it becomes a G code, then it becomes the actual geometry of the part and so forth.
You're recording some information from province, say, here's the thing that actually matters.
Yes.
Generically making policy.
Yes, yes. And we want to remove the manual part. Yeah.
Any other questions? Exactly 10 a.m.
Okay. Thank you all.
Thanks again for the speaker, and we have a present and something for her. And
Thank you
this
so
is
much.
Certificate of Appreciation, ACM WiSec 2022. It's presented to Gabriela Giappali,
Thank you so much.
right? And also here's a present from
Thank
the
you.
general.
Appreciate it. Thank you.
We'll have the break for 30 minutes, and you will come back for the, I think it's a machine learning session. And if you want to say something.
Three on-site speakers for the next session. Please quickly come and see me, and if you want to feel free to do so. Welcome everybody to session 3 of WiSec 2022. Session 3 is about machine learning and security, and we are going to have 2 full and 2 short papers in this session. The first full paper will be presented remotely. The other three speakers are on site. However, we have the first author presenter in the remote presentation of the first paper online and live. So if you have any questions after this first remote presentation, please just save them for a short Q&A directly following that presentation. The author will be ready to answer questions at this point. With that, it's my pleasure to introduce the first talk, which will be given by Wenqing Yan and is entitled RRF, a robust radiometric fingerprint authentication system that embraces wireless channel diversity.
Hello everyone, my name is Wenqing Yan from Uppsala University in Sweden. It's a pity that this year we cannot attend WiSec physically because of visa issues, but it's still my great pleasure today to present our research work, RRF, a robust radiometric fingerprint system that embraces wireless channel diversity. This work is done together with my supervisors, Timos and Kristen. So first, let's start with a commonly discussed topic, Internet of Things. Currently, tons of sensors and actuators are used to construct a pervasive virtual information net. For security reasons, in the Internet virtual world, identification and authentications are absolutely important, which helps us to recognize each other and ensure each device is who it claims as. Normally, today we can distinguish a device with its bit-level identities, such as addresses, MAC or IP address, or even more secure with certificates, which includes bit-level ID and keys for PKI usage to do authentication. In Edge network, each digital certificate is a file authorized by certificate authority, stored in each device, which needs to be exchanged every time when one device wants to communicate with another. So bit-level IDs are commonly used and are good things, but it is also easily to modify or replicate. You can change your IP or hardcode your MAC address with little effort. Besides, when talking about edge like wireless sensor network, we are talking about this kind of device. It is minor size with limited capabilities and even batteryless. So is there any better options for this kind of limited budgets? Bit-level IDs are something that each device knows. It is configured by us, human. This is also a reason why it's easy to modify. Could we change the security to be a function of what the device is instead of what it knows? Something like human fingerprint, which is widely used to achieve user authentication goal. Then we have the radiometric fingerprint for the hardware, which is imperfection of the hardware components. For people who work on the hardware design, we all know when looking through the datasheet of different components, the performance cannot be perfect, which is special for each component, even of the same type. And for wireless transmitter, this performance impairments will leave footprint in transmitted signal. Let's put it into the picture of wireless sensor network. When a sensing platform reports the collected data, it will generate a wireless signal and transmit out, which carries a fingerprint. The signal passes through the wireless channel and arrives at the receiver side. Then the receiver can extract out the fingerprint, which can be used as evidence to recognize different transmitters. Then, based on the application requirements, it can serve along other form of security protocols for authentication or identification usage. So the method can be used on low-cost end devices because it's just like human fingerprint. These are default characteristics and can be regarded as a physical ID of each individual device. So it's no need to store by the end device, update or maintain. And once the device transmits signal, these features are hidden in the signal by default. So there is zero extra requirement for resource constrained end devices. And as we described, the signal generated by the end device, which contains a fingerprint, needs to pass through wireless channel, complex wireless channels, then arrives at the receiver side. Then the receiver uses signal processing scheme to extract out fingerprints and pass it to the classification module with algorithms to achieve classification functionality. For us, it is a data-driven algorithm, and then it can recognize transmitter device. So the problem here is the transmitted signal is not directly observable to receiver. Instead, the receiver only can see a compound of the transmitter imperfection and the transit impact coming from the wireless channel. So the received signal is impacted by the wireless channel, so does its fingerprint. The imperfection might be small compared to the channel disturbance. In other words, the channel might hide the fingerprint, and it's really challenging to perfectly isolate out the transmit imperfections. So wireless channel not only impacts the transmit signal, but also the fingerprint. So the system design we introduce in this paper is aiming to solve this problem. And we design a system provides a robust identification or authentication service with radiometric fingerprints, even under complex channel fading disturbance. So first, let's look a little bit more why the wireless channel disturbance is a problem for radiometric fingerprint practical usage. We experiment with 1504 protocols for these 40 devices, including 4 types and each type 10 devices. We test our fingerprint system with support vector machine as classifier. In clean environment, it can easily reach above 99% accuracy, but it's hard to maintain this accuracy in real wireless environments. As we called clean environment, like anechoic chamber, is without refraction, no other coexisting signal, no moving object. But in real life, we have all of them, which will distort the fingerprint features and causing the accuracy drops. Then let me back up you with some experimental data. We test 4 scenarios in the same indoor environments for 10 devices of the same kind, and all of them are line of sight setup. So each device we collect around 3,000 samples. The first setup is when the transmitter is close, 50 centimeters away from the receiver. And the second, we move the receiver a little bit far, 6 meters away from the transmitters, which is the tested device, and across some furniture like the tables here. And next one, we keep the position of the transmitter and the receiver and change the furniture arrangements around. And in the final one, we ask 2 people moving around and create a bit dynamics in the environment. So here we use accuracy to quantify the system performance. And the accuracy of one device, the device I, is defined as the number of samples whose classified labels are equal to their actual labels divided by the total number of samples of device I. And the average accuracy is a mean value among all tested devices. And the worst case accuracy is the class which performs worst. And then we train the model with fingerprint samples collected in one setup and test in the same setup. The accuracy is pretty good, over 99% for both metrics. However, this performance cannot maintain when testing other scenarios. So for example, here we trained with the data samples collected in the setup 1, and we test in other 3 setups. The accuracy drops a lot. And even for these 2 scenarios, where we only change the table arrangement a bit, small difference in the same room leads to big distortions in the fingerprint. Which means like actually the model trained in one context cannot handle well in others. And for some devices, the worst case accuracy indicates that it's even hard to get one sample correct. And when we trained with dynamic environment here, which cover a time-varying channel, the performance is better. But there is no guarantee that it can cover all potential cases. Collected data from many environments or potential environment is also really clumsy and not realistic, especially for a large number of devices. And how to train a classifier to work in an unknown environment is also a question. So here I summarize the research problem a bit. So we can achieve good classification accuracy, which means radiometric fingerprint works, but it's hard to maintain this accuracy over multiple measurements in different wireless environments, which makes it very challenging for practical usage. So how can we solve it? Before we find out the solution, let's look a little bit more details how wireless channel distorts the fingerprint. So let's start with the features we use in our research. So this figure will show the source of transmitter impairments, which including symbol rate errors from the clock, modulation error from IQ modulators, frequency deviation and phase noise from the oscillators, and spouse tones from the mixture and power amplifiers. And here is a short overview of the features we use. 5 classes we get from the receiver demodulation process, and is commonly shown in previous fingerprint papers also. So the first one is fingerprint, the feature frequency offset from the synchronization stage. And second one is also the focus is a constellation-based features. And for 15.4, it's QPSK. So after we synchronize it, we get a synchronized constellation which has 4 clouds. And we quantify its IQ imbalance and also phase and magnitude errors. And the last one is a correlation features based on the SFD, which is start of the frame delimiter, which is common for every packet. And in order to learn about the impact of channel on fingerprint features, we look from 3 major channel factors, which are multipass, noise, and Doppler effects from moving objects. We leverage a series of channel simulation to systematically quantify the impacts. So we collect the transmitted signal with IQ format in clean environment. And then we pass it through the different controlled wireless channels to learn the details. So first is multipass. We use two-ray-rice model and refer to the empirical indoor channel statistic reported by other paper to choose the parameter ranges. And the major observation we made is constellation-based features and the SFD correlations are susceptible to channel disturbance. A more severe multipass channel leads to a higher constellation-based features deviation as well as lower SFDC. Besides, multipass impacts fingerprint features are not at random, but in a very distinct way. With linear transformation, we can project the features into 3-dimensional space and visualize it. We randomly choose one device here. The observation I present holds for all devices. The gray cloud is the decision zone of the specific device, and the black is the fingerprint samples collected in clean environment. The simulated fingerprint we show in colors, and we can observe it forms a fan shape with different trajectory. We notice that second pass delay leads to the different trajectory, and how far it deviates from the ideal samples on the trajectory depends on second pass signal strength. And next we move on to noise. So we use additive wide Gaussian noise models, and noise is inevitably challenging the demodulation process and results in higher random noise left in a synchronized constellation, which increase the variance across samples for all constellation-based features. And SFD correlation is a matrix that directly quantifies the difference between measured samples and ideal signal, so therefore it is susceptible to the noise. And in 3D feature space, we can see low signal-to-noise ratio, where leads to the simulated fingerprint forms a sparse cloud because of the increased variance across features. Besides this cloud, it slightly deviates from the ideal samples in one direction, which is due to the shift of this SFD correlation features. And the last one is Doppler, because of the moving objects. And the Doppler spread challenges the resolution of the carrier recovery algorithms in the coherent demodulator, which naturally disturbs the frequency offset features. But it barely drags the fingerprint samples out of the decision zone. And for common indoor scenario, it's actually very uncommon to have a level of Doppler shifts more than 80 Hertz. Because for 80 Hertz, which is corresponding to 2.4 gigahertz, the speed actually is 10 meter per second, which is really fast for indoor scenario. So in this common range below 80 hertz, actually most features are stable. So in our system design, we ignore this aspect. And based on these insights, we present RRF, a system that ensures the fingerprint classification do a better job and provides a robust identification or authentication service even under complex channel fading disturbance. And in our system design, we add 2 stages in the processing pipeline. The first stage is priority training, which is designed for manifest impacts. And the second one is noise compensation, which is for the weak signal. And the core idea of the simulation-aided prior training is to utilize wireless channel knowledge to simulate fingerprints under different multipass channel conditions before practical usage. So our system will generate a hybrid profile for each enrolled device, including the enrolled fingerprint which is measured and 50 simulated versions under different multipass channels. It is a data augmentation process which we can optimize the decision zone and guide the classifier fit better the practical multipass environment, which we'll show in the testing scenario. So in the identification phase, the classifier can implement the transfer knowledge learned from the simulation into the real world. And for the noise composition, we have 2 parts which based on the 2 major observations. The first one is this SFD correlation decreases when the signal is weak. And this feature is correlated with the signal-to-noise ratio, like the figure shown here. And the relation actually is independent of the device type. Then we can use this SNR as an indicator to compensate it. And second is based on the observations that noise will increasing the variance across the samples of all constellation-based features. For this, we deploy a sliding window on fingerprint samples before passing it to the classifying identification phase to reduce the variance. And then we move on to the final section, evaluation. We evaluate our system both with simulations and practical experiment in a series of indoor environments. The simulation evaluation of for 40 devices. The first part is mainly evaluate the priority training. So we generate a test set of fingerprint samples, 500 samples per device with randomly pick up channel parameters. And I only present average accuracy here. For more metrics, you can find in our papers. And we can see the devastating impact on the multipass channel without prior training. But in contrast, prior training leads to significant improvements and system reaches an average accuracy of 98%. So with prior training, our models has higher tolerance and robustness towards with multipass impacts. And then let's move on to the next section with focus on the noise. So we generate the test set by adding Gaussian noise to the benchmark IQ samples. And then finally test set, it includes fingerprint samples extracted from frames with different signal-to-noise ratio, randomly picked from 5 dB to 40 dB. And comparing the baseline, hybrid profile implementation already improves the average accuracy by 18% with only one single sample. And our complete RRF system can optimize the average accuracy even further and reach an average accuracy of 99%. And then we move on to the practical experiments. We test in 3 environments with 13 different setups. The first one is the same as the preliminary experiment I presented before with 4 setups. The second is a rich multipass environment in a narrow aisle with many metal tubes suspended from the ceiling along the wall, and which leads to complex multipass effects. It's more close to the industrial factory. And line of sight, and we use a line of sight setup, and we test full distance up to 20 meters. And we also including a moving transmitters, which mimic the wearable or moving objects. And last one is office corridor with non-line of sight setup. So we put our transmitter devices in one of the office with the door closed. And then we put our receiver at different distance up to 20 meters. And we also include the wearable scenarios. So here is an overview of the results. So the data set is the same, around 3,000 samples per device. And during the comparison, we can see without RRF, the wireless channel in real-world experiments severely challenging the fingerprint robustness. So it barely can achieve an acceptable accuracy. But with RRF, it achieves a constantly good performance for both average and worst-case accuracy above 99%. And here is all my presentation. I want to conclude this presentation as follows. First, in our research, we analyze the impacts of wireless channel on fingerprints. And we use systematically designed simulations to get insights how the channels impact the fingerprint features, and which allows us to design a hybrid pipeline that embraces the distortion caused by the wireless channel and enhance the system robustness. And finally, based on our evaluation in both simulations and with practical experiments, we demonstrate the RF design achieves a good accuracy in a variety of wireless, everyday wireless environments. And we also demonstrate the system design can enhance the robustness of radiometric fingerprint system. Thank you for listening. If you have any question, feel to drop your question to me.
And if there are any questions already, please step up to the microphone. I think we have more microphones.
Thank you for the great presentation. I really like it. My question is that, so in your method, you kind of bring the understanding of the wireless channel and then how it behaves to the machine learning training data set. That's how you incorporate your domain knowledge into the machine learning training process. And I'm wondering that this is, I think it's a smart way. So you generate a more generalized data set for the training. But I wonder if there's any way that we can, another way of incorporating that domain knowledge into the machine learning process.
Another way. So actually, at the beginning of what we want to try is not a kind of like we are not going to the like data augmentation direction, but we're trying to like building a models and you directly find the relation about wireless channel, how they directly impact the features. So by doing that, you don't really need to put into the simulation to generate the simulated version. You can directly foresee how the features will change in which directions. So that will be a less complex way in terms of like computational complexity. So but that's also challenging because kind of like you need to have a really perfect model to foresee like how the wireless channel can precisely change different features in which way. So the performance of that models actually is not that great compared our simulation-based data augmentation way. But I foresee like that is another way to implement. Or another way to do the data augmentation.
Thank you.
Do we have any immediate other questions from the audience? Okay, I have one question. Since it's in the title and the paper that this one particular use case might be as an authentication system, using the radio fingerprint for authenticating devices. Do you have any data or any gut feeling of how easy it would be for malicious attackers to try and fake particular fingerprints? So those features that you're extracting, that you're using for the identification, which of those would lend themselves to specific tampering by an attacker with, let's say, a slightly more capable transmitter?
So in our paper, we also have a section to discuss the security aspect. So actually, our paper is fingerprint system. The titles there is actually not accurate. So we discard this authentication part. The reason behind is exactly about defense, the attacker, which might show for authentication or identification case. We have several cases we need to discuss. The first case is, of course, like a device which already enrolled in the system. So a malicious attacker probably just kind of steal this device, control this device, and try to impersonate another device already enrolled. And that kind of attacker is not a problem for fingerprinting in general and also our system. But another more tricky question probably is unenrolled device. So if attacker which is haven't seen by the fingerprint system and he tried to initiate attacker attacks and to attack the system, that probably will be a problem, but it quite depends on the algorithms we are implementing, the classification algorithms. So for our implementation in the paper, we mainly use SVM, and that we have a problem, like because SVM is more permissive. So kind of like an unseen device will be classified as one of the device. But we also propose another two layers like distance-based methods to reduce this risk, like it be treated as one of the device, because kind of we observe kind of the SVM decision zone is kind of larger than the training samples zooms. So actually, that is why it's permissive. So we can use a kind of training samples to shrink the possible sample showcase to make it more kind of reliable in terms of this unseen device. But it quite depends on the classification algorithm. For example, neural network would need another solution to solve this unseen device problem.
Thanks a lot for that clarification. Do we have one other question in the room? No, not at this time. If you have further questions, please feel free to reach out to the authors through email or other channels. Thanks a lot again to our speaker. I'd like to welcome our second speaker on stage. The second paper will be a short paper presentation. Our speaker is from INSA Lyon, and Samuel will tell us about their paper on device re-identification in LoRaWAN through messages linkage. And it seems we are ready to go.
Nice.
Stage is yours.
Thank you. Okay, so good morning, everyone. My name is Samuel Pellissier. Today I'm going to present to you our work on device identification in LoRaWAN through message linkage. It was done with Mathieu Quinge, Vincent Roca, and Didier Donzé in France. So quick words of introduction. It shouldn't come as a shock for people in this room, but IoT devices are used everywhere today. There are more than 10 billion of them worldwide, and 225 million of them are LoRaWAN devices. When we think of IoT, we may think of smart homes with ways to automate lighting or manage the watering or electric systems. but the applications are much broader than this. We can indeed monitor the health of people. We can track cargoes around the world or crops in the field. And we can also manage electricity or water. And with great connectivity comes great responsibility. So we still more than ever have to protect the privacy of users. Even though IoT devices can be using wires, today's talk is focusing on identifiers in wireless network protocols, and more specifically in LoRaWAN. And in this case, there are ways to track the user's position. It has already been done with Bluetooth or Wi-Fi, for example, to track the user in shopping malls. As said in the previous talk, we can also use the radio signal features to fingerprint devices. And finally, we could infer activity through metadata. For example, if a garage door is connected, the existence of only one message is enough to know that the owner of the house is leaving or coming back home. More specifically, in LoRaWAN, we can use the identifiers to gather more information about the end device and its application. And we can then map it to an already known identity, activity, or location. For example, if we know that one specific company is deploying some kind of end device somewhere, we can take the traffic of this end device and linking back to the actual identity of the company. This is a sort of passive collection. It's quite cheap for an attacker because gateways cost around $100 to $300, and it's quite easy based on the nature of the protocol. Because LoRaWAN is part of a bigger family, which is the LP1 for low power wide area network. There are lots of protocols in this family. You may have heard of Sigfox, NB-IoT, -7, and LoRaWAN. They are long range, so a few kilometers. They have a low bit rate and a low energy consumption. And finally, they are mostly low cost. So the end devices operate somewhere in the wild. I've forgotten there for a few years on battery. This is a typical architecture of a LoRaWAN network. On the left, you can see the end devices. They are connected through a radio link to gateways, which then translate this radio signal into a classic IP TCP packet. And it goes all the way through various servers. And then the servers can treat the data and answer back to the sensors. For today's talk, there are two relevant identifiers. The first one being the DevUI, which is unique for the lifetime of the end device and set by the manufacturer. And you can view it as a kind of MAC address. And the second one is a dev address, which is randomly generated for each session. So each time the end device joins the network, there is a new pseudonym generated for it. Below is the global way, the most used way to join a network. There are different types of servers here, but only the join server is relevant for today. So first of all, the end device sends a join request containing clear text, the DevUI. This goes all the way through the join server that identify the end device. And if the identification is correct, the join server answers back with the join accept containing the encrypted version of the dev address. So then the end device decrypts the dev address and can use it in the upcoming communication. So in every single following message containing data, which is called uplink, there is a clear text version of the dev address. So from an outsider perspective, an attacker that listens the radio link in between the end device and the gateway, there is theoretically no way to link back the join request with the following uplink, and thus the dev UI in cleartext here with the following cleartext of the dev address here. And what we're trying to do is basically this. To do so, we have a quite simple threat model. The end device is left unmodified and the payload stays encrypted. So we only deal with the radio and the clear text that goes over it. And the attacker is passive, which means they do not inject or alter any message. They can only eavesdrop the physical link in between the end device and the gateway, and they can control several gateways. And as a side note, the fact that the LoRaWAN is long range only increases the attack surface. It doesn't really change the fault model itself. So how can we do this? We have to consider that we have a data set of messages. In our experiments, we use a dataset with the ground truth, so we already know the links. And in this dataset, there are two types of messages. One type is the join request, and the other are the uplinks. So we pick one join request, and we want to find the following uplink that corresponds to the same end device. To do so, we can use some data from the header of the messages. For example, there is something called the frame counter, which is increased every time one end device sends a message. So it starts as 0 and then goes up. So we take one join request, get the following uplinks, and try to find one uplink that has a frame counter equals to 0. So this means the join request and the uplink have a high chance of coming from the same end device. Another way to look at it is to check the timing in between messages, because one end device do not have any incentive to wait after receiving the join accept. So the join request and the following uplinks are quite close time-wise. We can also look at the radio signal features because we consider that each end device has a kind of radio profile. So two messages coming from the same end device should have the same radio profile, so the same radio features. For example, in this illustration, the end device 1 is farther away from the gateway than the end device 2. So there should be a difference in RSSI between those two end devices. So we once again take the list of messages, we pick one join request and try to look for more or less similar radio profile in the following uplinks. And we can then link back the two messages. This is the whole list of features. I won't go into the details here. There are 4 categories, one being the radio, another one being the actual modulation of the signal, the LoRa signal. Another one is the information contained in the headers of the LoRa one. And finally, we have some application specifics about the timings. All these features are then used to train a classification model. This is a classic binary classification problem. We use various classifiers on the right here. The goal is not really to compare them, but rather to find one for which the attack is working. And that's the case. On the left here, we have the various classifier and the true positive rate as well as the false positive rate. And we can see that multiple ones provides interesting results. The true positive rate is quite high, and the false positive rate is really low, which means we have a high confidence on the result that we find, on the links that we find. During this process, we have found that the frame counter plays a great role in determining which link is or is not correct. So we try to remove it. And this is also the result on the right here. We can see that the true positive rate drops quite a bit for all the classifiers, and the false positive rate remains the same. This means that the frame counter could be used as a countermeasure. To do so, we can encrypt it or try to start at the random offset. So instead of starting at 0 for for the first uplink message, we could start at a random value determined during the joining phase. As a side note, this is not backward compatible for the current standard. We could also try to introduce some randomness inside, for example, the radio features, but changing the radio signal power may make us lose some messages. We could add some random delay in between the join accept and the following uplink, or pad the payload, or maybe use multiple first uplink messages, and some of them would be decoys. But all these solutions introduce a lack of performance in the protocol. And finally, as we are dealing with identifiers, we could try to obfuscate them. And one way to do it is to use reservable addresses, such as in Bluetooth Low Energy, or maybe to use a shared address for multiple end devices, and then server-side use the network session key for identification. And once again, this is not backward compatible. As a conclusion, we have shown that we can reliably re-identify devices using various features. The frame counter is greatly responsible for the attack's performance. And finally, the countermeasures that we are proposing often require to change the lower one specification, as well as reducing the performances. Thank you, everyone. If you have any questions, I'll be glad to take them.
Thanks a lot for that short presentation and with very dense information, I have to say.
Yeah.
Do we have any questions right now? So one thing that stuck to me immediately when you mentioned it's not compatible with your mitigations are not immediately compatible with the specification. I have to admit I'm not overly familiar with LoRaWAN. So those changes that you propose to the spec, could they be introduced incrementally? Could that be done on top of existing networks where you can protect singular devices that use your adapted specification while still remaining compatible with the rest of the network? Or would you really need a changeover day to switch from one spec to the next spec to do that?
No. Actually, it depends on which thing we want to implement. For example, if we take the frame counter one, we could use the random offset directly. So instead of starting at 0 for the first uplink, we start at, I don't know, 100 or random value, right? So this is already supported by existing networks. We could use this directly today, but other things may require to change and may break the compatibility with previous version.
Okay, so the other changes would really require changes to the gateways, not just to single devices.
Yeah.
And those changes to the gateways would then break communication, potentially break communication with non-modified devices.
Yeah,
Is that right?
more than the gateways, it would be the various servers that you're using. The
server
LoRaWAN.
side.
So,
Okay.
yeah.
Would that work with? Does LoRaWAN have a version identifier in some of those protocol fields? Could you do?
Yeah.
Could you run
Yeah,
two
we could
protocol versions in the
identify
same
which
network?
version and then redirect the
So
message.
servers could have a fallback to
Yes.
other clients.
And I think in some implementation that's already the case between the 1.0 version and 1.1. So,
Right. Okay, so most of your do I get this correctly? That most of your changes could be added to existing networks without breaking non-modified devices.
yeah, but I mean, yeah, it still needs to be a new version of the standard.
Got it.
Yeah.
Are you in contact with the standardization committees?
Not at the moment, but
Okay, is
we'd like to.
Is that
work
a
on it.
plan
Yeah.
to maybe get a new version
because
there?
we have we are still working on other problems
Uh-huh.
with our spoilers, but that will be a good thing to actually work on the standard next.
Excellent. Do we have any other questions at the moment? Again, if you have any later questions, please just reach out to the authors through email or any other channels. Then thank you very much again.
Thank you.
Our third talk in this session is again going to be a long presentation. A long presentation entitled P-Act, Detecting and Classifying Privacy Behavior of Android Applications. Oh, beautiful. It's already there. And given by Shananda Gupta. So I think there's nothing else to say. The stage is yours.
Thank you. Hello, everyone. So today I'm going to present our paper that is PACT, Detecting and Classifying Privacy Behavior of Android Application. So developers are often required to provide privacy notices to the users so that users will be aware to know how and why their information is being used. So in order to do so, developers usually use policy generators to generate privacy policies, one way of providing privacy notices. However, these policy generators often do not capture the true privacy behavior of an application. Thus, as a result, the generated privacy policies become inconsistent with application's actual privacy behavior. Moreover, developers often use third-party libraries to provide certain services without properly being aware of their privacy configurations. These third-party libraries accessing users' personal information might also affect the application's privacy behavior. In many cases, developers often do not include privacy notice as a part of software engineering artifact, and thus many applications don't even have any privacy notices. In previous work, several research have been attempted to identify inconsistencies between an application and its privacy policies. Such as a series of work by Zimek et al. Actually identified that there are inconsistencies between an Android application and its privacy policy. And by inconsistency, I mean that your application is collecting your location, but it is not even mentioning it in its privacy policy. In order to address this challenge, several works have been attempted to generate consistent privacy policies based on either questionnaire or predefined templates. However, to the best of our knowledge, none of this work actually resolve the inconsistencies, or they do not provide any traceability. And by traceability, I mean that the generated privacy policy does not have any link with the application source code. In order to address these research gaps, in our previous work, we introduced an approach called Prigen. So what Prigen does is it identifies and extracts code segment that uses personal information. In this work, we call such code segment as permission returning code segment, or in short, PRCS. After extracting PRCS, Prigen basically translates it to its corresponding privacy captions. And here, privacy captions are short descriptive sentences that are describing the privacy behavior of a certain code segment. For an average length of 4 to 5 lines of code, we actually achieve very good accuracy. However, and this approach actually provides us traceability because we know which source code has been translated to which privacy caption. And it also resolves inconsistency because the privacy caption is generated directly from the source code. However, we faced some challenges, such as the accuracy started decreasing when the length of code started increasing. Also, if we want to train a large deep learning network, we actually require a high quality large data set that is, 1, time consuming to annotate, 2, it requires huge manual effort. Moreover, privacy perception may vary based on individual to individual. In this case, creating semantically similar privacy captions for a certain code segment can be challenging. To address these challenges, as well as maintaining consistency and providing traceability, in this work, we propose PACT, or Privacy Action Taxonomy. PACT basically aims at identifying privacy behavior of a mobile application. In our work, we focused on Android-based mobile application. So the question can arise that what do we mean by privacy behavior? In this work, we consider privacy behavior of a code segment is the practice and purpose of using that information. So by practice, I mean that how a code segment uses your personal information, and by purpose, why the code segment is using this personal information. So PACT basically provides us a lot of benefits, such as it may include a set of labels that can describe practice and purpose. So an annotator can basically use these labels to annotate the code segment that actually elevate the privacy subjectivity. Also, since we will have a set of labels, it is easier to label a code segment than generating semantically similar captions that might require a lot of time to do. PACT basically includes 3 important steps. First, we need to identify the labels that can actually describe the practice and purpose of a code segment. Then we are aiming to conduct experiments to see that if we can automatically identify those labels in a code segment, then we analyze the results to find out the limitations or rooms that we need to work in the future. So first, let's talk about the identifying the labels. In order to identify the labels, we focus on PRCS, or permission recurring code segment. Let me discuss a little bit about what PRCS is. So in Android application, if we want to access a certain information, we basically need to use Android API. In order to preserve privacy and protect privacy of an individual, this API requires permission to be mentioned in manifest.xml. So what we do is we identify such code segments that call such permission recurring API, and we call such code segments in general permission recurring code segment, or PRCS. So a PRCS can have multiple methods linked via call graph, and each method can be referred as hop. So for example, first hop is the first method that is calling the permission recurring API, and the second hop is the second method that is calling the first hop to call that the first hop that is calling the permission recurring API. So in our work, each PRCS can contain up to 3 hops. Why? Because in our primary analysis, we actually analyze that 80% of the time information has been used within the 3 hops of our PRCS. We also developed our in-house PDROIT static analysis tool and use that tool to extract PRCS from Android APK files. So in next slide, I'm going to discuss how did we identify the labels from the PRCS that can describe the practice and purpose of an Android application. So we basically followed the conceptual to empirical approach that has been introduced by Nickerson et al. And which is widely adapted to generate to basically develop any kind of taxonomy. So first, we actually we basically collected an initial set of labels from several privacy regulations such as GDPR and CCPA, and also Apple's privacy nutrition label. Then we used our PDROIT static analysis tool to extract a set of PRCS. We analyzed the labels. We looked for certain end conditions. If the end conditions met, then we will stop the process. Otherwise, we will update the label set, and then we will extract another set of PRCS, and the whole process continues until we meet any end conditions. The end conditions could be no new label can be introduced, or we don't need to update the current label set. After we meet any end conditions, we basically finalize our label set. The whole process, including the end conditions and the iterations, everything is available in our paper. If you're interested, you can just go over it. So after 3 iterations, we basically identified 4 labels for practice and 4 labels for purpose. The first level for practice is processing. That is when a personal information is being used to provide certain information. For example, a ride-sharing application might collect your location, and it might use this to provide nearest ride. The second level for practice is sharing. That is any third-party library is accessing that Android API. The third level is collecting. That is the accessed information is being saved in any off-device location. Apart from these 3 levels, we also decided to have another level other when the usage of the personal information is not clear to us. Similar to practice, we also identified 4 different levels for purpose. The first level is functionality, when the information has been used for the app's functionality purposes, such as location, payment, or authentication. The second purpose level is basically advertisement, when the information has been used for advertisement purpose. And the third is basically analytics, that is the information has been used for analytical purpose, such as crash analytics or user analytics. Similar to the practice, we also introduced another level, that is other, for purpose, when the purpose of using the personal information is not clear to us. So now we have 4 levels for practice and 4 levels for purpose. The next stage for us too, we wanted to annotate certain PRCS with these 8 levels. So for that, we relied on Android dataset. It is a very popular dataset that has more than 3 million Android APK files. We extracted randomly 15,000 APK files, and then using our pDroid, we basically extracted 180,000 PRCS. The first 2 authors of the paper, using our in-house annotation tool Coder, that I will come a bit next, we annotated 5,200 PRCS with the identified levels for practice and purpose. It is to be noted that each PRCS can have more than 1 level. I mean that one PRCS can have sharing and processing as practice level, and also can have advertisement and analytics as purpose level. Now the question can be, how did we annotate the code segments? How did we understand that a PRCS can have basically sharing level or processing level? We basically defined a set of heuristics. The details are in the paper. Let me briefly explain, go over it. So we basically looked into a lot of cases, such as the name of the classes, the method, the API name, as well as the description of the API. We also traced the flow of the information within the hop as well as the between the hops. We also looked into the types of the third party. For example, if the third party is for advertisement purpose, or if the third party is an analytical third party. Let me walk you through an example to understand it a bit clear. So this is one PRCS. The blue box denotes the method, that is get connection Wi-Fi info. And the red box basically denotes the Android API that has been called by the get connection Wi-Fi info. In this example, that is get connection info. And the green box basically the variable that is storing the information that has been received by calling the Android API. Now, if we take a close look at it and analyze the flow, we can notice that this information has been used to get the MAC address and IP address of the device, and it has also been returned to further hops. So from this analysis, we can conclude that the practice of accessing this information is processing. We can also label sharing because the class name and the APK names are not same. And that means that the code segment is from third party. If the code segment is supposed to be from first party, then the class name will be derived from the APK name. And the purpose we have labeled is as advertisement because the third party library is an ad library. As I mentioned earlier, we used our in-house annotation tool Coder. The reason we did not use any existing tool because to the best of our knowledge, no existing tools actually provide annotation for source code. Coder basically helps us and supports us in various ways. You can basically do classification, translation, and annotation tasks. Multiple annotators can actually work on the same project. And also you can actually you can have control over the annotator's roles, and you can define certain permissions. And also you can host the tool in a private server that can also ensure your privacy. So this is the user interface of Coder. As you can see, the code segments fit perfectly, and it is true for any programming language. We also provide the APK metadata, and the metadata includes various types of information, such as the APK name, class name, and the method name, as well as the API that has been called. We also provide the API description that is similar to the description available in Android public documentation. We can also see the collapsible bar for second and third hop. And you can also see that we have label drop-down box that has basically the label and that we have identified for purpose and practice. You can also see the guideline dialog box. So any annotators can, during the annotation time, can just look into the guideline to get some idea. There is also a navigation button that will help any annotators to go back and change the annotation that they have done previously. So using this annotation tool, we have basically annotated 5,200 PRCS, as I mentioned earlier. Now the next step for us to conduct certain experiments to answer 2 research questions. The first research question focuses on what is the baseline accuracy to identify individual practice and purpose labels in a code segment. And the second research question focuses on if we increase the number of hops, if it has any impact on identifying individual practice and privacy labels in PRCS. So in order to actually answer this research question, we need to develop 2 different datasets for each of these research questions. So first, let's discuss about the dataset that we developed for research question 1. So as I mentioned earlier, research question 1 focuses on baseline accuracy that to identify individual practice and purpose labels. Remember that each level, practice and purpose, each of them has actually 4 labels. So we have in total 8 labels. And our PRCS can have more than 1 label annotated to it. But here we are only focusing on identifying individual labels. So in total, we have 8 labels. So we decided to actually develop a 8 binary dataset. So the question then may arise that how did we make the binary dataset of a code segment that is already annotated with multiple labels? So let me give an example to it. Let us consider that there is a PRCS that is labeled with sharing and processing. So what we do is, we first make a copy of it, and for sharing binary dataset, we consider sharing as positive and all the other labels that are not assigned to it as negative. For processing, the same principle has been followed. We consider processing as positive and all the other labels that are not assigned to it as negative. It is also need to be mentioned that for research question 1, we only considered code segments from first hop. Now let's talk about research question 2. Research question 2 focuses on that if increasing number of hops have any impact on identifying individual practice and purpose labels. We have in total 3 hops, as I mentioned earlier, and we have total 8 labels. So we have in total 24 binary dataset. Now the question is, how did we make the dataset? First, we collected all the code segments that we used in research question 1 that has up to 3 hops. We filtered them out, and if any code segment has more than 1 label assigned to it, what we do, we actually follow the same principle we did for the research question 1. For sharing dataset, binary dataset, we basically consider sharing as positive and all the other labels not assigned to it as negative. And this is true for 3 hop samples. And another thing to be mentioned that for research question 2, we have first hop that has only code segments from first hop, second hop that will have code segment from both first and second hop, and third hop will have code segment from first, second, and third hop. Once we develop the datasets, then we extracted AST path and binary label, and we feed it to a simple RNA network with PRCS embedding, and we calculated our metric scores and generated confusion metric for research question 1 and research question 2. This is our model architecture. We have embedding layer that is embedded with the AST path. Each AST path has 3 tokens. And then we basically concatenate these 3 tokens into a single vector. And then we feed it to a fully connected layer F1. Then we use the output of the F1 as to 2-layer LSTM model. And then basically we use the hidden state of this LSTM as an input to our output layer F2. And then we passed it through a sigmoid optimized function to optimize the binary classification and prediction. Now let's discuss some results that we found interesting and we wanted to share with you. So let's first discuss the result for RQ1. Research question 1 focuses on the baseline accuracy to actually identify practice and purpose levels. And this is the result for both practice and purpose. And from the table, we can see that across the level types, we found good F1 score for the collecting, that is 79.62%. And for purpose, we found a good F1 score for functionality, that is 79.02%. Now let's take a closer look at it. So for collecting, that is a level for practice, if we take a close look at the confusion matrix, we can see that 84 samples have been identified as true positive and 67 samples has been identified as true negative. That basically demonstrates that our model is optimized and it is not actually biased towards any positive and negative samples. But we actually received a bit different result for analytics, that is the level for purpose. We noticed that we got F1 score 66.88%, and it is, again, let me recall you that for research question 1, we only considered the first hop code sample. And the confusion matrix shows that our model is biased towards the positive samples. One reason we did not receive the moderately good result for analytics could be that it is from basically third-party libraries, and often cases third-party libraries basically uses the information in further hops. Now let us discuss the result for research question 2. And as I mentioned earlier, research question 2 focuses on if increasing number of hops have any impact on model's performance while we are actually predicting the individual levels for practice and purpose. So this is basically a result for the practice, and we can see that we actually in first hop for processing we received 58.75% accuracy, but once we basically gave the additional information, that is the second hop, the accuracy increased a bit and we received 64.75%. However, the accuracy decreased a little bit once we actually introduced another hop, that is the third hop. So the reason could be processing is a very complex task. So you need to look at different cases such as the calculating your location or changing values or retrieving certain information. So it might be one of the cases that we did not receive better result for processing. However, okay, so for sharing, we noticed that the more hops we have introduced, the model could predict better, perform better. So for example, for sharing, in first hop, we received 65.1% accuracy. We introduced another hop, the accuracy increased and we received 67.1%. And then we introduced further hop and then we actually received 71.09%, which is pretty good. And it also aligns with our understanding that sharing is basically the code segment from third-party library. And it might be the case that third party is basically using this information in further hops. For purpose, this is the result for the purpose level, and we can see that we are getting pretty good accuracy for the functionality, and that is 86.97% in second hops, and the accuracy slightly decreased in third hop. So one of the reason could be that functionality is basically the first party code segment, so they might have basically used this information within the first 2 hops. And if you remember the result for analytics and analytics for the research question 1, from research question 1 to research question 2, we actually received better result in further hops. That is 78.83% in both second hops and third hop. That actually also aligns with whatever we are assuming. That is, it might be that the third-party code segments are using your information for analytical purposes in further hops. And this is the confusion matrix for the processing level. And as I mentioned earlier, that processing is a complex level to predict, and it would be worth exploring that what are the features that have been used to actually predict and why we are getting such a result. And for functionality, we received, if we take a closer look at the confusion matrix, we can see that our model actually predict a false negative and false positive for the lower amount of code segments. That actually shows the effectiveness of our model. In conclusion, I want to say that yes, we introduced an automated approach that would actually detect privacy behavior in Android application. And to the best of our knowledge, we are the first one so far to develop a taxonomy to identify privacy behavior specifically in source code. And we also annotated 5,200 code segments with the practice and purpose levels that we have identified. And we conducted experiments with 8 datasets in 4 configurations. And we actually achieved better F1 score 79.62% and 79.02% across the level types. For future work, as I mentioned earlier, each PRCS can have at least more than one level. And in this work, we only focused on understanding if we can predict the individual level. So in future, we want to conduct multi-level, multi-class classification experiment. And we also focus on using larger models such as convolutional graph neural network. And we also noticed that for certain levels, we are getting better result. And for certain levels, we have to sort of compromise. So we also want to see that what are the features that have been used for classification tasks. And for that, we are planning to actually study attention. And this overall framework is focused on helping developers to generate accurate and consistent privacy notice. So we also aim at conducting user studies with developers to know that how do they actually perceive the effectiveness of our framework. With this, I conclude the presentation, and I'm open to any questions.
Thank you. Do we have any questions? You mentioned on future work already that you will be looking into multi-class, multi-label classifications. Are you intending to look at all combinations of different labels, or specifically the cross-product between purpose and practice? If so, if there's a specific cross-product of purpose and practice labels, do you identify any combinations that are particularly sensitive or that would be the typical okay category? So if you look at the multi-label, multi-class, what specifically are you looking for?
That's a great question. So in future, we are actually planning to look into all the labels rather than cross products, because you know that a code segment has certain practice and purpose. So we actually want to look into that if if our model can predict multiple levels for both practice and purposes. So we are not actually looking to the cross product. We are looking into all of it.
Do you have any preliminary data, any teaser of would that probably improve accuracy? Do you think that if you actually look at multi-labels, that you could get even better results? Or is it going to be even more challenging because you've got less data samples for those combinations of labels to train on?
It's an interesting question. I might have to look at it. I don't have the answer at this point, but that might be the case that it might also, our dataset might also, if we change certain bits, such as we actually used, for research question 1, we actually used the first 100 AST path. And for research question 2, we randomized the AST path. So maybe in future, if for the same dataset, we change the combinations of the AST path, that might also actually improve the accuracy, but this is something worth exploring.
Do you expect that you will need to manually annotate even more samples to get sufficient data size for training for the combinations of labels?
I don't think so at this point, but even if it requires manual annotation, I think annotating labels are more time efficient than actually generating privacy captions or something. So, and we also have our in-house tool, so which is user-friendly, so that should not be a very big challenge for us.
Okay. Any other questions at this point? Yes, please.
Thank you. If you can go back to one of the confusion matrix slide, the very first one, it was very interesting. Not many research teams show the false negatives. I appreciate presenting that because it has value, not only just showing the positive results, but negative results help folks not to try in those areas. So I appreciate that. But one of that had like 101 and 105 as, yeah, for the analytics. You mentioned the true reason for such high false negatives is some third-party libraries. Can you clarify more or expand more on it? Like, what is the primary reason for such high false?
So I okay, I most probably did not actually explain it better, I think. So for the confusion matrix, I mentioned that our model is a bit biased towards the positive samples. But if you look into the analytics, that is basically the level for purpose, we received 66.88% F1 score, which is definitely not a very good one. But this is something we can see that we can improve maybe in future. So one of the reasons could be that because analytics are basically third-party libraries, which means the third-party code segments are basically accessing those Android API. So maybe that the third-party libraries are using those information in further hops. And if you look into the result for research question 2, where we basically used first, second, and third hop, the result of the analytics actually improved. That is 78.83%. So that could be actually a reason that we're not sure about it yet, but this is something worth exploring.
Thank you.
Any other questions? Not at this point. Again, if you have later questions, please just reach out through digital channels. Thanks again to our speaker. And we come to the fourth and final talk of this session, which is going to be a short talk again, entitled Bias Hacker, Voice Command Disruption by Exploiting Speaker Biases in Automatic Speech Recognition, given by Peyton Walker. So let's do the typical projector dance. Where is it? I feel like HDMI cables are the new printers, right? Never works on first try. There we go.
Did you open it?
After this session, we'll actually move into the lunch break. Lunch break will be 90 minutes. And afterwards, please join us for the panel discussion. The panel discussion specifically on, well, sorry, I just messed up my schedule here. Yes, I was looking at the specific title. Yes, the panel discussion on wireless and mobile security research and teaching in the post-pandemic world. So I think we've all experienced some parts of it, and I'm looking forward to the panel discussion to try to consolidate some of those experiences. Now we're up and running. The stage is yours.
Thank you. Hello, everyone. As you mentioned, my name is Peyton Walker. I'm from Texas A&M University, and today I'll be talking about our work where we explored a potential attack that we call Bias Hacker that looks to exploit existing speaker biases in current automatic speech recognition systems for command disruption attack. It's not moving. No. Perfect. Oh, hit the slide.
Did you keep, what's happening?
I tried hitting enter next and it's not moving. It's not. Next button works. It would be my presentation that wigs out. All right. So this work is firstly motivated by the fact that racial and gender biases are a known issue in multiple types of recognition systems. And this persists even among current state-of-the-art technology in devices and other tech that's available and comes out today for our use. And in terms of machine learning, this can be caused by multiple different problems. There could be feedback issues if you've got bias in an original model that feeds into a newer updated version. You could have biased learning algorithms if you optimize for error rates. And in terms of the marginalized groups that suffer from these biases, there could be inaccuracies in ground truth labels or just poor representation of those groups within the data themselves in terms of quantity or quality. And specifically, we see these biases persist in speech recognition systems. And this is particularly concerning and relevant considering how quickly these devices are becoming more popular and the growing number of options we have in terms of voice controllable systems. And so not only personal assistants that we install on our phones, but also smart speaker dedicated devices that fully run on these recognition systems. And the presence of these biases leads to low performance and usability for certain groups. And in terms of security, when we think about potential threats and attacks against these systems, it becomes more severe considering the adoption of smart home environments. So now we're connecting multiple different IoT smart devices that control some very critical operations within our home environment, like smart locks, security systems, or even smart appliances. And the typical form of attack against speech recognition systems and with these smart IoT devices is to typically inject a command. So an attacker tries to issue their own command, hopefully going unnoticed, and that allows them to, in a way, control the device and use it for their own purposes. But in this work, we actually consider the potential threats and devastating impacts that can occur when certain critical commands get disrupted. And so when a user tries to issue a command and that gets blocked from happening. And so if you imagine trying to, lock your doors with a voice command at the end of the night and that command gets blocked, then your house is left unlocked throughout the night while you're going to sleep. So specifically, also looking at the attack potential for command disruption and incorporating these and exploitation of these existing speech recognition biases. So this figure shows our attack design. So firstly, we consider we have this legitimate user who's trying to issue a vocal command to their voice assistant or smart speaker device. And this legitimate user can come from an underrepresented or marginalized group in terms of speech recognition performance. And on the other side, we have an attacker who uses some method to construct a disruptive chatter type noise that'll be played kind of alongside the speech command and hopefully block it. And a typical approach to generating these chatter noises is to combine samples of not only plain speech, but music and then some sort of static noise like a Gaussian white noise. And so we imagine that if this chatter noise that's being created incorporates speech content from a speaker type that doesn't suffer from these biases, then when it's played in the presence of legitimate speech from one of these marginalized groups, then the voice assistant can actually give some sort of preference when it's trying to process the audio. So because of that, you could have a legitimate command being completely ignored and it attempting to process and identify the speech that's contained in the noise sample. And whether or not it's actually identified or results in anything, the main issue here is that the legitimate command gets ignored. So our methodology was to create this attack through experiments and demonstrate using kind of over-the-air instances. So firstly, we looked at 2 instances of live smart speakers. We used a Google Home Mini and an Amazon Echo Dot. And since we're looking at potential bias exploitation and the effect it can have in this attack, we consider multiple different victim speaker types. And so using Google text-to-speech API, we generated 22 speech samples of from different speaker types for a smart speaker command for each of these devices. And we included representation for not only female and male speech, but also American English accented speech, which represents that kind of not biased speaker class that doesn't suffer from these issues. And then a few other accents that don't have as good a performance. And so British, German, Korean, and Australian. And also in line with looking at potential bias exploitation, we generated 3 versions of this disruptive chatter noise that an attacker may try to use. So of the three main versions, we isolated kind of three small samples out of the larger disruptive noise that was created because it's designed to just be played over that quick part of the vocal command from the user. So we had a total of 9 samples, but the 3 types of disruptive noise we created was one, looking at American English male speech and music-related content, again, representing that type of speaker that may get preferred and cause this kind of command disruption to be successful. But also wanting to observe the effect of 2 other types of speakers that can suffer from these biases. So we had one based on a female speaker with a Nigerian accent and a female speaker with a Korean accent. We tested 3 different volumes for playing this noise. In all of our experiments, the regular command, plain speech command to the smart speakers was played at 70 decibels. So we just tested different levels of this disruptive noise at 50, 60, and 70. And for each of these kind of combinations, we ran 10 trials. And so that led us to conduct almost 12,000 different attack attempts. And for each one, we recorded whether or not command disruption was successful. And successful command disruption could be not only straight up getting the legitimate command to be ignored and nothing happening on the smart device, or it getting misrecognized as something else or something that's not useful or doesn't achieve the desired result. So this table summarizes our results in terms of scenarios where we saw instances of successful command disruption versus no success at disrupting the command for each of the different smart speakers and speaker types and noise types that we looked at. These results are specific to the experiments where the noise was played at 60 decibels. So one thing that we found afterwards was that at 50 decibels, the noise just wasn't loud enough to cause any command disruption. So no success throughout. And then at 70 decibels, when it matched the volume level of the speech, it was too loud. And all of the different sample types or noise types would mask the all the different user commands. And so at 60 decibels, though, we do see some variation here. And although we see, kind of varying levels of average accuracy and success between different speaker types and things like that, really when we start looking at the patterns of where we see instances of success versus no success is where things start to get interesting. And so from these results, we make a few main observations. First is that there's clear evidence of racial bias specific to the Google Home Mini device. The success that we observed was limited to only non-American English accented speakers, meaning, didn't matter the gender, but command disruption only worked against the different accents, not including American English. On the other hand, we saw very clear evidence of gender bias for the Amazon Echo Dot smart speaker. Here, success in terms of command disruption was limited to only female speaker samples, and this was true for all the different accents that we looked at. And then lastly, by comparing the performance of the different types of noise that we used in our experiments, one thing that we observed that was true for both smart speakers in all scenarios was that the American English male version of the noise outperformed the other non-American English versions, suggesting that the speech content and accent there does play into the success of the noise and could be some evidence of bias exploitation. So in this work, we presented Bias Hacker, introducing this kind of new attack that uses specially crafted noise and exploits existing biases for this command disruption-based attack. We evaluated 3 types of disruptive chatter noise against 2 live smart speaker implementations and confirmed presences of known racial and gender biases that we already suspected. But we were also able to demonstrate that the American English male version of the chatter noise representing that non-biased speaker type was more effective than the biased accented versions of the noise that we use, specifically on the Google Home Mini compared to the Nigerian accent and Korean accented female versions of the chatter noise. The American English male version improved upon attack success by 112 and 121% respectively. And on the Amazon Echo Dot, it improved attack success by 42 and 69%. So if anything, our results reveal that there's certainly threat potential there for this type of attack and exploiting these biases. And some viability. And it's important to note that this attack can be launched against any voice controllable system. It doesn't just have to be a smart speaker. Anything that accepts these critical commands could be exploited in this way, as long as they're using a speech recognition system that suffers and still maintains these biases. So for future work, we're planning to look at more sophisticated techniques for noise generation, which can obviously lead into additional attack goals. So generating a noise that not only blocks a user's command, but you could potentially, slip in a command intentionally that you want to have recognized. And then obviously by demonstrating that this biases can be exploited in this way, it opens up another line of research in terms of potential defenses. So thank you.
Thank you. Do we have any questions already? Yes, please.
I have two quick questions. The first is just a technical detail. Was the noise, the speech noise, also generated via text-to-speech?
No, so the disruptive noise, we sourced the plain speech samples from TED Talks, videos of TED Talks available on YouTube, and then also music videos available on YouTube, just specifically looking for ones that correlated with the speaker type we were looking for. And then we generated the Gaussian white noise sample and just combined the three of those using a software called Audacity.
Great, thank you. I'm also curious about the timing of when the disruptive noise is played. For example, if you interrupt a command halfway through, how does that affect the viability of this attack rather than interrupting the entire command?
Yeah. So for our experiments, we specifically designed it and played it in a way so that the noise was played to overlap the command part of the speech. So when you issue a command to a smart speaker, you give the wake word, and there's like a small, 1 second gap of time, short space, and then the actual command part. So in our experiments, we just for simplicity and because it was a scenario we could reproduce, we used the hang up command for like an active call scenario. So we had the devices connected with an active call to another smart speaker, and the user's trying to issue a hang up command to end that call. And so what we did was we had it play the wake word so that it gets activated, and then the noise itself was just played over that one single part of the command. In terms of it being successful with just masking part of it, I would suspect that there's certainly potential there, depending on what part you can copy, or can mask. So if you mask like the first half of the word, it can be harder to identify the word based on the last half, but also depending on what the command is and the system, Google or Alexa's like recognizability with that command. They still may be able to recognize it. Because one thing we observed was that like the wake word is actually pretty well recognized even under like noisy conditions compared to actual like command part of the word. So just depending on what it is, it could still be successful if you mask just part of the word.
Other questions?
Thank you for the presentation. How audible would be this attack? So if I say a command and then I hear there's like some noise coming in, I would recognize it, or is it like very silent and still?
So we're imagining, well, first thing is our results showed that this can be successful when the noise is 10 decibels quieter than the normal speech. And so depending on what scenario you're in, obviously, depending on the user, if you're hyper aware or if you like live in a house just that's completely silent all the time, you would absolutely notice that some random noise got injected. But there are also a lot of use cases. Like me, I typically always have a TV on in my house somewhere, music playing, something like that. And so in those cases, you could slip in this like small short bit of noise that would go, seemingly benign. And depending on the type of, static noise you may include into it, you can make it sound like, a lawnmower going off or a train horn or something, which those are noises that you think you'd recognize, but like in actual living situations, they're very benign in the sense that you don't really give it a second thought when you do hear them. You're just like, oh, lawnmower, move on to the next thing. So depending on the scenario, yes, it could be recognized, but we imagine obviously this to be applied for attack scenarios where a small bit of noise could go pretty undetected.
Any other question at the moment? Is it possible that those recognition systems are tweaked towards better recognizing live voices than those generated through WaveNet?
I'd like to say yes, but actually no, from what I've seen. So one precursor to the accented versions of the command speech that we use was that we tested them all without any noise. We confirmed that all of these, machine-generated speech samples did have 100% accuracy when you play them without any presence of noise. And I'd like to think that in a situation where if you have live speech compared to like a machine-generated noise, that it would be able to distinguish the two. But on that same note, when I'm at home just talking of a conversation, my devices will wake up to something they hear on a commercial. And so I don't think it's definitely possible, and you can certainly distinguish between live and injected noise in that way, but I don't think it's currently implemented in these recognition systems.
And do you have any data or suspicion if, because the chatter noise was one male, American accented male, and two female accented voices. Is it possible that the different frequency ranges just make the male voice more likely to be successful as a chatter noise? So did you also try it with the Nigerian male accented voice, for example, to see if that changes the results?
We did not. We did do a sort of kind of pre-inspection of these different versions of the chatter noise once we created them, inspecting them in the frequency and power spectrum domains to confirm that there wasn't any significant kind of differences in the frequencies that were present. Obviously, with live human speech, there are those distinct frequency differences between males and females, but for machine-generated
one octave
speech,
difference.
Yeah. And in the presence, it being something that combines like a Gaussian white noise that has like a full frequency, masking spectrum, we just, we ensured that in terms of the frequencies that were present and when it's being played, there weren't that significant difference. So I think it does have more to do with the actual pronunciation of words and things like that that make them more identifiable.
Got it. Any other question? If not, then thanks again.
I think we have. So I think we're actually have the tools to go ahead and mitigate something like this. It's just kind of taking the devices one step further. So for instance, on current smart speakers, I think in the past year or two, they've had this voice profile feature implemented on it. And so you can train your voice profile so that if were to order something for shopping, it recognizes your voice and it uses your payment and shipping information versus like your roommate or something like that. But it's not, the capability or the options aren't there to say, this is my voice profile, only respond to my voice kind of thing. And so if you just added that kind of one extra bit of permission, I guess, on your device to say, like, here's my voice profile, and I want you to prioritize my voice over anything else you hear, no matter what. I think that would be a way to mitigate something like this. And yeah, so something like that. Yeah, and obviously, if you can fix the biases in the machine learning and improve the model so that they're not like that, that would be best.
Thanks again.
Thank you.
I think that's just opens lunch. Or do you have any other announcements? Then enjoy your lunch and see you at the panel. Thank you.
And we'll be continuing on to our next part of the conference, which is a panel on how the pandemic has shaped our research and teaching lives. And we have 4 panelists, fortunately. Unfortunately, Patrick could not make it in person, but as you see, his head is on the projector, right? So, so Rini here, he graciously accepted my very last moment invitation to serve on the panel. And I'll introduce all of our panelists one by one. So first off, we have Ahmed Reza Sadeghi, who is in TU Darmstadt. He is a full professor of computer science at TU Darmstadt in Germany, where he heads the system security lab. Since 2012, Professor Sadeghi established a long-term cooperation with Intel. He wants it to be short. He has worked with a lot of industry partners, in short, and mostly in telecom. And lately, he has been working in machine learning stuff as well. Then we have Gabriela Charcolier. Keynote speaker to the morning. She's an associate professor in the Department of Electrical Engineering and Electrical and Computer Engineering at UTSA. And she is also the Vice President of Secure Automation and Secure Manufacturing Architecture for Cymanel. Her expertise is in anomaly detection, distributed alert correlation, network and application level security, cyber physical system security, and distributed system security. Then we have Patrick Tate on screen. He's an associate teaching professor in the Information Networking Institute at Carnegie Mellon University, the Silicon Valley campus. Patrick leads the mobile, embedded, and wireless security group at the CMU Silicon Valley campus. His research interests closely align with his teaching responsibilities and includes things like wireless, mobile, and IoT security and privacy, wireless communication and networking, robust and resilient network systems, and analysis and sense making of data from sensing devices. Last but not the least, we have René Meyerhofer. He is both a professor at the Johannes Kepler University, and also he leads the Android platform security at Google. And I was just talking with him about some of the things I do with my phone, and he did support the things that I do are okay to do with it. His research includes usable security, networking, mobile computing, and ethics in computer science, and digital identity. So, like I said, the topic of this panel is to talk about how the pandemic has shaped our lives around the research and teaching that we do in this community, and with these experts in the area who have not only background in academia, but have also worked with industry partners, right? And that's why I believe these panelists could give us insight on how and what are the challenges they have faced and how they have gone about doing research during the pandemic, and what lessons can we take forward, not just in pandemic situations, but what are the good things that we learned over the last 2 years or so. All right, so the way we'd go through is that I would introduce particular topics, and I'll ask each panelist on their experiences and their thoughts, and then afterwards I would open the floor for questions to the audience, and if you have any questions, you can ask the panelists directly, right? All right. So the very first question I have, and this is based on some of my personal experiences as a junior faculty. Oh, by the way, I did not introduce myself. So I'm an assistant professor of computer science at the University of Oklahoma. I was actually a postdoc at UTSA for 2 years before I joined my current position. And I do privacy and security research in a broad area, of network security, side channel inference attacks. Recently, I'm also working on blockchains and NFTs. Yeah, so coming from my personal experiences as a junior faculty, I had a lot of difficulties in setting up research projects, and I had to pause certain projects because I just did not have other certain resources that were unavailable to me because of the lockdowns, or things like user studies had to be stopped because IRB would not approve certain things for user studies. So my question to you is that were there any projects that you had to pause during the pandemic, and what were the reasons behind it? And some of the reasons I could think of is because of behavioral changes, and that means that some of the things that we did during the pandemic were different from other times, and that would change the data that you collect, right? And that could be in terms of, let's say, mobile networks. How we have been using mobile phones did change during the pandemic because of mobility changes. And if we had collected data during the pandemic, there might have been some bias introduced in your data. And as if you have those biases, your results may not be reflective. So that's just one instance. So so in summary, do you have any projects that were also in such a similar situation where you had to pause the project until the pandemic was over, or you had to adapt it in an extreme way to make your project happen?
Really? Are you sure? Maybe you want to. Okay, so.
Okay, I can talk a little bit. Maybe our own bandwidth got limited during the pandemic, I don't know. But the project themselves, I think we managed. So if I'm talking with respect to Saimeni, right, this is intended to be a project collaboration across different organizations. So somehow we were set up for that. But of course, there were people who were helping us with the experiments, with using the machines on the floor and generating data and so forth. And they could, and they got the permissions to access the machines during those times, and everybody acted in a very safely manner, and we succeeded in doing our experiments. Probably one thing that is a little bit more difficult is to interact with students in person, and that's probably something that happened across all of us here. But projects can be done even in COVID times. No.
So I think for computer scientists are very much affine to being lonely. So it doesn't matter if there is war out there or there is a virus surging. We don't care. So I think this is what mentality that I experience, although I'm a very communicative person, but I experienced that most of my students were kind of, I mean, I don't know if they really needed psychological help because they've worked for me. So if they decide for me, that means they don't really need any help. And a number of projects were paused because of data collection. So if you do IoT projects and you have, let's say, 60, 70, 80 devices, and you put it in the different houses from different people, not only the students, that will be paused because going to the homes of people, installing stuff, that's difficult. But in general, for me, it was positive because I could really take care of the things that I could not take care of before. For example, my garden. And for students was good because they had to be kind of on their own somehow, except virtual communication. The only thing that I agree with is this personal touch, that you can go to the student, to the office of them and say, because we don't have really PhD students in Germany, it's more research assistants, and annoy them with where are the results, submission deadline is coming. Virtual, after a while, you just don't like it anymore. So I think that was the only problem. But in general, it has a positive and also negative. And also the number of cyber attacks got very much increased, which means we will be further in business. So for us, it was always good.
there were no projects that were actually canceled or paused on our side as well. We were in the weird situation that with 1st of January 2020, we actually started a new research lab that was just at the beginning of this crazy pandemic at the moment. And this was on digital identity. So so while the project wasn't canceled, it proceeded mostly as planned. We had, I think, two main challenges that were caused through the pandemic. The first one is probably shared by everybody. It was quite a lot harder to onboard new stuff. And since that project, the whole research lab just started 1st of January 2020, we always knew that the first 6 to whatever months would be taken up by onboarding by startup. That was delayed. So getting new staff into the project, being able to integrate them with a new group that they haven't been with, that was a main challenge. And still 2 years later, I think we are still slightly suffering from that because the team building that I would have done in the first year, that was delayed. That was not canceled, but delayed. And that does have probably some result on project outputs, even if that's not measurable to a certain extent. The second impact was because of our project setup. One of our main project partners there is the Kepler University Clinic, which is the medical research branch of the main hospital in Linz. And we actually intended to test some some authentication schemes, biometric authentication schemes in clinical settings. With all the, at least at that point, we assumed that face recognition would be harmed by masks. Well, then everybody had masks and we had to look at that anyways. But also other stuff like, can you do fingerprint recognition and so on. And we wanted to specifically go to the clinical setting because of the sensitivity of medical data that people are dealing with. That has been completely paused. So that one activity has not happened yet. Not because they didn't want to, but the hospital obviously was busy with other more important stuff than helping our research. But besides those two impacts, I agree. I don't think that in our computer science projects we were impacted all that much.
Patrick, you want to add something, Patrick?
Yeah, so I think from my side, the main impact was really just that all of our IoT focused projects really transformed into home IoT projects. My PhD student's kitchen turned into his lab because we lost access to all of our other lab facilities. So I think that was the main impact, and I think it worked well for him. And you'll see some of his work tomorrow. But I think that was the main one for us, other than really just not seeing everyone for a long time.
Right. Thank you. So not a lot of disruption, it seems. So my second question is kind of on the other side. That were there any projects that were inspired by the pandemic? And in fact, in our group, so I was working with some of my PhD students, and we had some actually interesting papers that came out based on the things that followed the pandemic, like virtual meetings and all. And we have a paper being published next month in DSN about virtual background reconstruction or real background reconstruction based on the imperfections in the virtual background rendering. So without the pandemic, probably we would not have had that idea. So is there any project ideas that you had during the pandemic or because of the pandemic? Yeah.
Okay, this is a long story. I make it very short. So in January 2020, I came back from Beijing, and as I was there, we heard that there is something coming up because I have colleagues. I worked with them in Wuhan in the past, and we heard something is coming out, and World Health Organization is going to announce that the pandemic is coming up. And for me, it was an interesting experience. So I was thinking about, because I've heard that in Singapore, in Vietnam, and in Korea, people started because they were really concerned with all these different diseases in the past. So they started to use different digital technologies to trace the pandemic, to find the infection chains, and so on. So I called the Ministry for Research in our state in Germany, and I asked them, we need to do something if this pandemic is going to spread. And it's maybe we can help from computer science department to do something based on what others did in other countries. And they said, okay, thank you. Don't call us, we call you. And they assume that this is a completely crazy professor, has a crazy idea at night, and then he wants to money from us. This is what most government agencies think, yeah, because that is the border of their thinking this, not going over that. So there's a limit there. So we started with digital contact tracing, and beside us, there were 100 other groups doing the same. And the German government and the lobbyists started to push digital contact tracing, which was at the end based on Google and Apple interface. And we started a public fight against giving access to data to Google and Apple. Why should European community agree with an interface made by Google and Apple? Because Google is a fantastic company. I must say, disclaimer, this is not what I say. This is not the view of TU Darmstadt. Apple is a fantastic company, but they are just taking our data, and I'm absolutely against it. So this is, oh yes, absolutely, yeah. I know them as well, so I don't think about that. So there are so many papers that you can read about this. And of course, it led to publications with also some of the people who are sitting here, because we were, so to say, in kind of David against Goliath. Yeah, so that was a good experience for me to see what is the power of lobbyists in any country that I had experience with when it comes to using technology. That was very interesting experience for us. We lost a lot of time, and a lot of students were working on that, but we had very nice papers, and we were the only ones, besides some people, some of colleagues in US, some of colleagues in Italy, in Spain, who were really in France, fighting against this.
Nice intro. I was part of the discussion on the other side. So yes, of course, the obvious one is contact tracing. That was, I think, that one technology that so many of us in this community were looking at. It was the obvious thing. And the numbers coming out of the UK and some other countries, I think, proved the technology right in the sense that it actually had some real world impact. There are some statistics that assume life saved globally in the ranges of hundreds of thousands of people through those contact tracing technologies. So this was an important thing to jump on, and that's why many people did it. Yes, those discussions were fierce. And as I experienced those academic discussions, papers against papers, and sometimes not very friendly words, I think the main discussion item was, as we sometimes have it, centralized versus decentralized, with very interesting trade-offs for contact tracing. They were not easy questions. The Google Apple proposal won simply because of how it could be deployed, because of rollout, because those companies could push it to a high percentage of phones that were in the market with reasonable, I would say, trade-offs for power. Other apps had the problem that they couldn't do the background scanning as well as the operating system services, so it was a power trade-off that had to be taken. But it was what was designed was a decentralized system. And funnily enough, some countries opposed it because it was decentralized data handling, because the health organizations in those countries actually wanted to have the centralized view to better be able to steer pandemic measures, because they would have had a better overview. With the decentralized data collection, it was really just up to the devices to warn their owners that they might have been exposed, and they could optionally upload that data and optionally like send the data for central analysis for a better global national overview. So that was part of the opposition, that privacy was taken too far. Some countries wanted to have more data than this solution actually provided. And yeah, since I've been part of that discussion, I can attest that the privacy measures were actually in place and they worked. And before rolling that out, there was a couple of months discussion on how to mitigate the various attacks. And I think that succeeded. As mentioned, for some countries, it succeeded too much because they didn't get enough data.
Yeah, Yeah, I think in the US, I would just want to add the fact that it took us a little bit of time to make the applications for the vaccination. That was maybe a little bit too slow. And I remember that it was easier for me to set up the appointments for my parents in Romania than it was in the US for myself. And I found that a little bit strange, let's say. So what else? One thing were the vaccines, one thing were the contact tracing. Even the vaccines have a particular privacy leakage. I understand that. Not everybody should see if you have or not have that particular password. So we have to be careful with how we present the data. Maybe we should think about technologies that are going to show something. Even if you didn't vaccinate, you still show something. So nobody who sits behind you will know if you actually got vaccinated or not. That's another way of handling the privacy.
That's another interesting point, the vaccination certificates. That was another fierce discussion that happened a little bit later than a contact tracing discussion. And on the EU level, I also think that the right decision was taken. It was the privacy-first design that was taken for those vaccination certificates, with very hard discussions because it wasn't an easy binary decision. There were trade-offs to be made. The trade-off or the decision made there was also for a decentralized system where all the information was encoded into the QR code and it could be read offline without having to go through central services. So again, actually taking away governments' capability to, through that, whenever you show your vaccination certificate, trace where it would be used or where people would, at which places people would show their vaccination certificates. So maybe one takeaway is that privacy actually took precedence in some of those decisions during the pandemic. And that was, from where I'm sitting, a good but unexpected turn of events.
About pandemic, I talked this morning about that paper on pandemic adaptive supply chain. So that's something that we should keep in mind for the next ones, because they will happen again, probably multiple times. So let's get prepared for that. I don't know, now people are talking about new types of vaccines, the nasal ones. There will be probably new factories set up, and we will need something similar to what I was talking about in the morning, so that we can switch to fast vaccinations and fast treatments.
Patrick, you want to add anything about the projects that you might have gotten inspiration during or because of the pandemic?
No, I don't think I have anything to add on that side.
All right, that was a very interesting discussion on getting ideas. And in fact, I also got a lot of free time because I was just sitting at home and I was thinking a lot. So maybe not directly related to the pandemic, but I got a bunch of ideas. So my third question is about the supply chain disruption. And this has affected me, and I'm pretty sure a lot of you, if you try to buy a Raspberry Pi, good luck. You have to probably go to eBay to buy a Raspberry Pi for $200. And I wanted to do certain experiments with embedded systems where my students wanted to have access to a Raspberry Pi. And unfortunately, that was a difficult task. And I'm sure some of you may have faced similar situation with other devices. If you have some kind of embedded systems or mobile systems with certain chips or transmitters, and if you are unable to get hands on those devices, you might have to find alternate routes, right? Things like, for example, emulating a network in order to carry out experimentation. But it may also be very difficult to emulate everything, right? Especially physical layer. How do you emulate physical layer stuff, right? And also, to the morning, Gabriela talked about pandemic. What was that? Pandemic adaptive manufacturing. And you are more focused on the biomedical manufacturing. Yes. So my question is about from the pandemic lessons, and I would say the effects are still ongoing because we still have a shortage of a lot of equipment. And I'd like you to share your experiences if you had faced any issues related to equipment, and how can we solve some of the issues that we are still facing. And that could include more general guidelines that you may want to apply, or just your personal opinions.
So again, the problem I mentioned this morning, in the Wuhan area, there are 50,000 companies that have the first year supply chain coming from one particular region. That can be a problem, and maybe there are other areas that provide a different kind of. So we in computer science, we always talk about decentralized systems, and this is exactly what we need to do. We have to think about the supply chain and actually have a way of decentralizing the supply sources, so that the supply chain sources, so that we have the ability to pull from areas that can provide those products. But then this idea of not keeping the full products, but keeping raw ingredients and being able to produce whenever we need, that's also key, especially in the pandemic, right? So we had the ventilators, and later on we didn't need them because we had different treatments. People were, there were new ideas on how to handle patients so that they don't need the ventilators. But then we filled up a lot of, we brought in a lot of equipment that was not necessary. So if we had a way of using the supply chains again differently and be adaptive, that would have been nice.
For us, only the, I guess, most trivial implications that it was harder to get servers, it was harder to get embedded systems for our experimentations. Maybe for myself personally, the most impactful thing was that I felt like I was constantly apologizing to my new staff members, again, building up a new research lab, that we had to give them 4-year-old laptops until we got the real ones that we had ordered 6 months ago. And of course, on some of them, we were still waiting for that. So I think we could deal with that. Luckily, we had enough hardware to get by. It just wasn't the nicest experience. Otherwise, to try and see the positive side of things, a lot of interesting supply chain security issues arose and maybe came more to the forefront. I don't know if it was related to the pandemic, but the last 12 months brought supply chain security, software supply chain security attacks to the main press. So we saw that in daily press. I don't know if that's correlation, but since we moved even more to digital services, of course, it was more an attack vector. So I think for us, trying to take the positive is it shone some light on what we all knew, and now we can actually convince people that you need to take it seriously.
So I think I make it short so that everybody here can ask questions, maybe if they are still awake. So for us, I think, and that's my criticism to most of our top security conferences, where the reviewers who give major revision to experimental papers where you need to have devices that are mostly coming from Taiwan or China, and they don't think about it and say, okay, make another 200 other experiments because I feel like it. And I'm a member of this community for many, many years, so I think everybody knows me, and I'm criticizing our community openly. This is going to be streamed? Anything that I say about any company is not right, as long as they sponsor this conference and me. So indeed, that was the biggest problem because the students. So we had to, let's say, you do experiments with electromagnetic interference, and you need the devices for that, and devices are made in Taiwan. Yeah. So how do we get the devices? There is supply chain shortage, as you mentioned both, and we had a problem in that sense. So we had to, people were really making their own devices. And then you come to the ethical problem because it's electromagnetic interference. So it's not safe if you don't know how to make it. Yeah? So these are the problems that came up for students. And I would rather protect the students and say, okay, forget about this paper and to, desperately try to get a major revision. So this is a message to all people who are in program committees. Don't overdo it. The major revision should improve the paper, help the authors, and not really torture them. It's not a psychological torture method. If you like waterboarding, go to military. Don't be a PC member, okay? Okay, thank you.
Patrick, you want to add anything about the supply chain disruption?
Yeah, so I think from my side, the biggest impact was on more on the side of teaching than on the side of research. So early in 2020, I agreed to redesign our embedded systems class. And that led to a really fun problem of how do I get the resources that I need? And since students aren't going to be on campus, how do we actually get some sort of embedded platform that is safe to use in a student's home when they can't get into the lab, when they don't have access to standard benchtop equipment. The solution we found was essentially moving away from the more mainstream platforms like Raspberry Pi and getting hardware from local suppliers. So we essentially got all of our hardware from Adafruit, which is in New York City. And so it's significantly more local than other places that we would typically get hardware. In the past, students actually fabbed their own or designed their own boards and shipped out their designs and had them made and shipped back to campus. That only works if you can do things overseas very quickly, which of course we can't do now. But the long short of it is we ended up with a really nice platform that was all sourced relatively locally. And that was the way that we were essentially able to get around that problem. And the other nice part of it was all essentially kind of hobbyist DIY style equipment. So it was very well suited for students to work in their home. We had some other challenges, like how do you actually get a benchtop setup that is virtualized that students can access online? That's something that one of my TAs actually designed as a side project, which was kind of fun. But yeah, so it was a really interesting experience. And I think the overall outcome was actually really great. It just took a lot of extra work to figure out how to do it.
Patrick, I have a follow-up questions on the things that you did, because I am also in a similar position, and I was also coming up with my own solutions. And what are the things that you would carry over even after, let's say, supply chain are better and things are in supply? And do you see some of these things you'd be using going forward forever or for the near future?
Yeah, absolutely. I think one one of the really nice things that came out of this is, the students that I work with are not electrical engineers. They're more computer scientists. They're typically more software-oriented people than hardware-oriented people. So I think one of the really nice things that came out of this was the fact that we needed to simplify things and we needed to get rid of some of the extra hardware. That's something we're absolutely going to be keeping. We built in some additional virtualization, and that, of course, is the best way to protect computer scientists from hardware is a little bit of virtualization. And I think everybody's going to enjoy that long into the future.
Yeah, thanks. That's what I'm also doing in a way. The things I have been setting up, a lot of virtual machines, virtual emulation stuff, which can be carried over in the education, like remote education and online learning. And about adding to the reviewer process, I do agree. Even we had a couple of major revisions where we were asked to do user studies, in fact. So it's a little different, but as little. Yeah. So of course those are not feasible, and we had to revert that it's not possible. All right. So with that, I would actually open the floor to questions to our panelists, and I'd put the mic in the center. And yep. Sorry. Oh, okay.
So thank you, the panelists, and for sharing your thoughts. So my question is regarding contact tracing. So we have spent enormous amount of financial and academic capital on this problem of contact tracing over the last 2 years, right? So I know NSF came out with this rapid proposal. There were several of them related to contact tracing. There was this entire wave with European researchers trying to do this from a privacy preserving perspective. There's a lot of work in the US as well. So my question is simple. How far are we from developing a perfect system? And then if we are hit with another pandemic, do we have an app because I have not used a contact tracing app in the entire pandemic. And if you have investors, and the way I feel about this problem is that these are not really new academic problems, really. Contact tracing, right? Ranging is one of the issues. Private set intersections, they've all been worked on. I think the problem that we're really trying to solve was of how do we bring this all together into a working system? So my question is simple. Are we there yet? So if let's say another pandemic hits in 2 years, do we have an app which
I think we should not. One thing is the computer science aspect. The second thing is as a society, are we ready to actually, this is something that actually connects us to save each other and respect each other and whatever. So I think as a society, we have to see it like that, to understand that we are helping ourselves, but we are helping our friends and neighbors and so forth. So I think this to me is the biggest lesson learned throughout this past year, more than the technology itself. This technology seems to be fine. The contact tracing, I traveled internationally. I was pinged in Iceland when it seems like somebody on my plane had COVID and things like that. But it's been working, and I would love to keep doing this, at least, if I know that I was exposed to whatever other virus we will have in the future, I know what to expect. I think knowing what to expect is actually a good thing.
Agreed. With everything said, I think there were not hard technical challenges that were foundational or fundamental that we didn't know before. Putting it together and rolling it out on a massive scale in a short amount of time, that was the challenge. And I think technologically we are in a good place. We could immediately start that up again on short notice. What went terribly wrong in the first place, and I'm not sure if we've learned our lesson, is communicating that to the public. So depending on, I've watched the communication of how that technology or how competing technologies were being introduced and explained to the public, and too many countries were doing a really bad job of that. And that was, I think, what broke public trust in many places in those contact tracing apps and why they were less effective than they could have been. And I'm not sure if we are ready for the next wave in terms of getting the communication right.
Exactly. So I have a different view to that. I think contact tracing apps are completely nonsense. And although we worked on that ourselves, and we had publication, we had tests on that, and we never wanted our scheme to be used by public because besides the problems of technology like brute to distance measuring false positives, we don't know, at least in Germany and also in other European countries, how effective these apps were. We still don't have any data about that. Yeah? And one thing that politicians learned is that, okay, you give it to your own companies in your country to get a lot of money and kind of self-contained economy. I understand this. This is you just protect your own company and then rely on a technology provided by Google and Apple because they can push, as mentioned before, push their phones to everyone if you have no other choice. Yeah? And the government told people and also other companies, many startups came with very nice ideas. And that is where standard comes in. You say, okay, you want a standard interface for privacy, but then get a lot of different ideas with the same interface that provides specific or fulfills specific requirements from the technological point of view. But from effectiveness point of view, I don't see any effectiveness, and there are also measurements on that. What is interesting is that people forget it and always play it down is the matter of relay attacks. Relay attacks are possible, and I can promise you we can make a very large-scale relay attack. But don't forget, this is illegal. Why is that illegal? Because as researchers, we know where we can do it. But if we do it, we are just stepping over a gray area because we are attacking a public health technology. That is how a lawyer would formulate it in front of the court. This is why we do not publish it or we do not say it, but we know that it is possible. And think about the government, an adversarial government, if you use these technologies in your phones and they want to provide fake infections. And that is very, very much possible. Although I know that Google and Apple played it always down because that's a very good way to do it. But it doesn't matter. I mean, they are doing business. I understand this approach. We are not doing, in that sense, business. We are doing what we want to do. So in general, it was very good aspect of it to learn things, new things, and understand who is profiting from what, who is really thinking about the public health and who not, how our politicians react to certain aspects. As I said several times, the role of lobbyists, I learned a lot how big their role are. I thought always they have an average role, but I think they have a big role even in scientific funding. And regarding the challenges of the technology, I think there were some interesting challenges on the other side, the reverse engineering aspects. For example, when it is only OS has access, the operating system, iOS or Android have access to those interfaces. How you reverse engineer those, that are some of the works were not published, but these are the things that we learned.
Patrick, you want to add anything?
Yes, I think that the thing I want to echo was just, I don't think there's really a huge technical problem with something like contact tracing. I think it's more of a cultural problem that we're going to face probably forever. One of the things we've really learned from the pandemic, at least in the US, is that a lot of people don't buy anything that's coming out of the media. They don't want to necessarily support things that are good for other people if they're not necessarily good for themselves. People who refuse to get vaccines, for example. And I think incentivizing people to opt into something like contact tracing is always going to be a problem. And until the vast majority of people are participating, I feel like the system is incomplete. So even if the technology works, the sample size might not be sufficient to really have a large-scale benefit. So I see it more as a cultural problem than anything else.
Thank you. Any more questions for our panelists?
So my question is more on the privacy domain. So we have contact tracing, and due to the pandemic, also in many countries, if a person is being COVID positive, they are required to wear certain wristband that will basically continuously collect their location for a certain period of time. And we have regulations like GDPR or CCPA. They have always emphasized on informed consent. So my question is, as a privacy and security researchers, do you think that in certain situations it is acceptable to compromise users' privacy because the situation demand, or if not, how we can basically tackle the situation by helping them in the urgency, as well as preserving their privacy and prioritizing their privacy perception?
That's an excellent question. I have to preface this with, I'm not a lawyer, and that's more a legal question than a technical one, because there is always this weighing of different impacts. And yes, of course, I think most would agree, most lawyers would agree that I talk to, that in certain exceptional situations, it is acceptable to, I wouldn't say break privacy, but to limit privacy or to limit other basic freedoms that we are typically used to in exceptional circumstances. Now, what we, I think, should take away from that as a community is, can we build technology that helps those specific circumstances in a way that the technology itself can be limited to only be used in those specific circumstances and then not be extended in a slippery slope towards ever more intrusions into other freedoms, privacy that we take for granted. And this is what was the basis for many of those fierce discussions that we were having 2 years ago of how do we build technology that helps in this case, but is not easy to abuse for other cases. And this is where lots of agree to disagree statements came out, because the trade-offs are hard. How do we technically limit something that is actually a legal problem if we don't trust policymakers globally to not abuse something that we introduce for exceptional circumstances? So I think many of us were towing the line of tipping into legal territory.
So I absolutely agree with it. It's the challenge of privacy technologies is that in my life, I worked in the past with a number of lawyers on different interdisciplinary projects, because we always propagate that we want to do interdisciplinary projects. It's not true in reality, but this is what university management tells you. But in reality, they don't really support it, because then they say, oh, funding, concentrate on one problem, don't give funding for so many lawyers. So, but it is very fascinating to see how lawyers argue about different situations and how scientists argue. That is what I found always very fascinating, because the problem that he was mentioning is, can you have a button that you just push so that the technology cannot be misused further, and it is only valid during that exceptional time, and afterwards you can just turn it off? That is very, very hard question to answer legally, but also technically. I think it's a big challenge for privacy. It was always like this. when somebody is in emergency, how you must access all the data of this person if this person is not in a status that he or she can react to what you are saying. So can you access all data? I think this is a challenging problem.
Who is turning it off? Yes. Yeah. Because in some countries it might be somebody, in other countries it might be somebody else.
We don't want to name countries, but some countries, one person decides that everybody else does. And in some other countries, they have a system that is based on arguments.
But then actually the trust plays a vital role here, that the information has already been accessed. Even if you turn the button off, if the company or the technology is only using this information for the purpose or not.
We have exactly that same kind of discussion right now again on the EU level, I guess on a global level, with a topic that is always coming up again because it hasn't been solved. The problem of scanning image material and text messages for, I'll call it unwanted material, depending on the local definition of what is not wanted in that case. And this has been, I think, has seen increasing attention also because of the pandemic, because we've moved to more and more chat and image and video messages during that time, and that is being used also by even younger generations. So the problem has definitely been aggravated. But we are currently having that exact same discussion of, hey, it's a real problem. We might want to accept that there are some limits to privacy or to other freedoms that we might accept to solve that problem. But how do we make it so that it can't be easily abused to extend the definition of unwanted material, depending on what locally is currently the policy. And those discussions are hard, they're ongoing, they're unsolved, because we're, again, trying to tackle a social, legal problem with technical measures. That's always hard.
So before maybe Patrick wants to say something as well, but one thing, as René was also mentioning before in the case of contact tracing, was how to communicate things to people. Yeah. And I think this is another challenge. It's maybe not a technical challenge, but it is indeed very hard to communicate things to people. As Patrick said, in the case of vaccination, we have it in Europe as well, people who are against vaccination. And I am really thinking of organizing a workshop, I seriously mean it, that people from Huawei and other telecommunication companies come and explain why 5G cannot make you sick by putting COVID-19 virus into your body through the 5G base channel band, whatever. Yeah, I'm going to organize and ask some experts, but this is exactly like discussion things with flat earthers. So there are lots of things that are combined with each other that people, even if you explain to them what is right from the scientific point of view, or maybe from legal point of view, they still don't want to believe it. So we have really fundamental social problem regarding privacy aspects and regarding freedom. What is freedom? Freedom is not that you have a mask because of public safety. Freedom is a much, much deeper meaning of that. But this discussion would not help us because we agree on it. But there are many people in this country and many other countries, they don't agree with that. So it would be nice if we also could know how to communicate privacy, technology, and the button case, and who pushes the button to people. Yeah, that would be great. So maybe Patrick wants to say.
I would just add one more word there. It's not only about the rights, it's also about responsibilities. I think people forget the responsibility part, and that's the sad part.
Patrick, you want to add anything?
Yeah, I think I just wanted to sum that up by saying I think technology is always going to be way ahead of any kind of regulation. I think that's one of the interesting things we've seen with CCPA is there are a lot of technologies out there that people are using on a regular basis that violate CCPA in really fantastic ways. And there's essentially nothing that the regulators can do about it because the technology already exists and people aren't going to turn it off. So there's always going to be this kind of concern over, is the technology right or are the regulations right? And who that's really up to is also a big discussion that is way over my head. But it's a super important thing to think about.
Thanks. Any more questions? Yeah, I always look at that outside.
Hi, everyone. So a quick question on, so the data right now, especially with all the pandemic, a lot of people are kind of forced to send everything in digitalized material and send it through non-contact ways. But there's issue with that, and I don't see a lot of people consider it, but a lot of the current encryptions are not breakable right now, but with quantum, it would be breakable. And some people are collecting all this data and waiting until encryption is breakable to break it. So what about our privacy 10 years later? Does no one care about that?
That's a very interesting question. Let's see how.
So this is why, so as you know, scientists and academia are extremely innovative when it comes to writing paper about any topic. So, and this is why we have post-quantum cryptography. So, and post-quantum cryptography, whether lattice-based or whatever scheme that people are using, is of course an emerging area, and a number of, I would say, beautiful minds are working on that. Many, many strong groups all over the world are trying to solve this problem after, Shor algorithm came up that, for example, many cryptographic assumptions like factorization or like discrete log, and the family of all those assumptions can be broken if one day, we have quantum computers, in the sense that it doesn't mean that quantum computers currently, they know what they are computing. It's not really about being faster, but sometimes they have a right answer. And when they have the right answer, then we are, so to say it roughly, we are screwed with all our privacy and unconditional, so to say, privacy is what we want. So we want to use an unconditionally secure or information theoretically secure, so to say, encryption scheme. But this is not what public key gives us, and this is why people are looking into the post-quantum cryptography. So that is a big research area, which is a very hot area.
Putting the security hat on, post-quantum cryptography is one of the few areas that does not actually let me sleep less well. Because here I believe that in security, it's one of the very, very few areas where the defenses are better than the attacks right now. And I expect that to stay that way for the next at least decade. OpenSSH, latest release of OpenSSH started enabling by default some post-quantum public key algorithms by default. Browsers have been doing experiments for that for a year. And any quantum computer that from an engineering point of view would be able to break even the most simple RSA keys is still leagues away, as far as we know. So here, defenses are actually more advanced than the attacks, which let's enjoy that as long as we have it.
Might be fine depending on the country. There are laws after how much time you have to trash the data. So keep that in mind as well. There will be only some data that could potentially be leaked.
Patrick, you want to add to that?
No, I think they covered it well.
Yeah. Any more questions for our panelists? Not, let's thank our panelists. Thank you.
Yeah. So I just want to make some announcements. Thanks again, all the panelists and India for moderating this panel. I think very interesting discussions. So just wanted to give you the schedule rest of the day today. We have a short half-an-hour break right now for coffee and some snacks outside. And then after that, we have one of the best panels, one of the best sessions of this conference, even better than the one Ahmad actually chaired yesterday. Uh, but that's on mobile security. And after that, we have a roughly an hour, 15-minute break where you guys can go to your rooms, maybe freshen up a little bit. We'll have the award dinner starting at 6. So what we'll do is we'll probably gather in this room, maybe 5:55, 5 minutes before the actual dinner time, where we'll probably make the announcements for the best paper, best demo, and best poster awards in this room. And then we'll have our dinner outside and go in the banquet. Right? Thank you very much.
Thank you. And thank you, Patrick. I know you probably don't see us. Maybe you see us, I don't know. But yeah, thank you for joining, and I hope you get recovered soon, right? Thanks.
Thank you.
And one more thing, the authors of the presenters for the next session, please come to me to the audio and video desk. Thank you.
The buffet was I went for the
So, welcome back, everyone. I am Eric. I am your session chair, and I am also the chair of the poster and demo session. I'm also doing some of the live streaming here. And I am now here with Nisha. Nisha is a PhD student here at UTSA, so she's one of the locals here. And she is doing a PhD about about something that not a lot of people focus on in the US, about pedestrians. She looks at the privacy and security and safety implications of technology on pedestrians. So you have seen the US as a country that is all about cars, but Nisha focuses on that very narrow spot, the pedestrian. Paper is not only written by her, but also by Raveen, who is currently over there at the audio and video mixer, and Anindya, who's currently sitting there. And he's also helping us with the organization of the conference, and Murtaza, who is over there, and he is the actual chair here of WiSec. So you have the whole crew on board. So now we will hear an investigative study on the privacy implications of mobile e-scooter rental apps by Nisha. And now the stage is all yours.
Thank you, Eric. Hi, everyone. My name is Nisha. I'm, like Eric said, I'm a PhD student from UTSA. So today I'm going to talk about my work, the investigative study on the privacy implications of mobile e-scooter rental apps. So micromobility. Micromobility is just, an umbrella term that you use to represent or denote a specific type of transportation option that you see in most of the urban communities. So micromobility essentially could be like people or battery powered. It could be docked or dockless. There are several types of micromobility that you would have encountered in most of the major cities, some including e-bikes, hoverboards, segways, and also e-scooters that you would have seen in front of the hotel, several of those. So a quick fact is that among all the micromobility types, e-scooters were the most used, at least in the US, up until 2019, based on NACTO's shared micromobility report. So you had more than 100 million trips just up until 2019, so it could be just even more than that as of now. So these e-scooters, they're available either for rent or to own. So most of these e-scooters, at least in cities like San Antonio, are available to rent by several service providers. So this concept of providing these e-scooters for rent was introduced in sometime around 2017. So how this 2017 came about is based on when the initial set of e-scooter rental services or the service apps were available in the Google Play Store or Apple Play Stores, at least to the general public. So if you kind of look at it, you have across over 100 unique service providers across the globe. Because of the pandemic, it may have increased or decreased. Overall, most of these service providers kind of operate in either multiple cities or even in multiple countries. And the one thing is that each of the service providers have their own apps. They kind of make available their own apps to the general public. And these apps, they could either deploy the same app across different countries, or they could choose to deploy different versions across these countries. So how do you essentially use this app, or for what you use this app is to essentially rent, like to start riding the scooter. The first step essentially is to scan the QR code using the smartphone where you actually install the app. And once you've done that, you can essentially start riding the scooter. So the problem here is that you have so many e-scooter service providers available. The problem is that if you're a user of more than one of these services, like one of the service provider could be like a Bird, Lime, and so on. If you're kind of using more than 2 or 3 services, there is a problem of data leakage between the apps, like the service apps, or from the service app to other apps that you have in your device. Another possible way the leakage happens could be via the API. So there are some service providers which kind of use the same company to host their backend. So that's where the actual API to API leakage may happen. The most important scenario is that where which happens offline without the user's knowledge, is when these services collect this information and share it with third-party entities. So these are 3 different ways that we actually think that data could be leaked, at least in the e-scooter service ecosystem. So to kind of study about, to kind of look into or identify these leakage scenarios, we kind of looked into the literature. As you know, as you can see, literature has like ample number of works just telling you how to identify all these sensitive data leaks and so on. And moreover, you have several tools which are publicly available just to analyze apps and privacy policies like overall. But none of these 4 works had actually extensively focused on how data-related practices occurred in e-scooter rental services. So that is why in this work, we're trying to assess what kind of privacy risks may occur by using these service providers, at least these e-scooter services. So to go with that, so we try to have or analyze the practices followed by these service providers across 4 objectives. So in RO1, we try to kind of look into the user data that is being accessed or collected by these service apps. And in RO2, we kind of look into the third parties which are kind of associated with these applications. For example, if you have a Bird, so Bird has an SDK, which, like for example, a Google Ads SDK. So Bird would be your first party, and your Google would essentially be considered as a third party. And then in RO3, we kind of look into the privacy policy document just to see if that users are adequately being informed about the practices that these e-scooter service providers kind of follow. And lastly, in RO4, we're trying to find if there is a trend across how these data sharing practices evolved since 2017 up until 2021. So, so to start the analysis, we essentially need a data set. So, so the way we shortlisted the data set is we specifically chose Android applications, mainly because of the open source nature of Android, and also we couldn't find any reputable repositories to download iOS apps. Another criterion we kind of used to shortlist the apps was that apps had to have English language support, because most of the tools that we used for the analysis did not support other languages. So that was also another criterion that we used to shortlist the app. Overall, we had analyzed over 102 rental services, which were there up until sometime around mid-2021. So as I told you, we had like 4 objectives. For the first 3 objectives, we kind of downloaded or used the apps, the latest apps directly from the Google Play Store, mainly because Androzoo only had applications from the .com store. So if we had to download some apps from the European or country Play stores, then that was not possible. So that's why we had 2 different data sets. So once we had all the apps downloaded, we kind of grouped them into 3 categories based on their download counts at the time of analysis. So any applications with more than 100,000 downloads would be considered most popular apps or service apps, and then anything with less than 10,000 downloads would be considered as least popular apps. So the analysis methodology. So the first thing, now that we had the data set, we had the apps, and then we also downloaded the privacy policies corresponding to the applications. So what we did is the first part, we're trying to analyze the applications. So the way we went about analyzing the applications is we applied several static and dynamic analysis techniques that we earlier saw. At least at a higher level, we monitored the API calls associated with the service application, especially during runtime, mainly to identify the user data points that we need to focus on later on. So some of these data points could be something from plain text strings, obfuscated identifiers, even SQL database files. So once we have that, we try to apply data and control flow techniques, also available in the literature, either using the chosen tool set, or manually, just to identify two different things. So the first part is identifying the user data related practices, and the second one is essentially identify the presence of third parties in these applications. And the next a component that we analyze is essentially the privacy policy associated with these applications. So in the privacy policy analysis, we essentially try to find what type of information is available in these privacy policies, and do they sufficiently cover their data handling practices or not, or users informed of their rights related to the data and those kind of aspects. And finally, we combine all the results from the app and the policy analysis over time, and that's where we try to identify trends, which is in the fourth research objective, RO4. So all this analysis was done in 64-bit desktop computers and also on actual smartphones, using the tools that you see on the table on the right. So among all the tools, policies was something that we used for policy analysis for all the policies that were not handled by policies, such as policy documents in different languages or in PDF format. We had done the analysis manually. And all the other tools that you see, apart from the highlighted ones, were used for the application analysis, the static and dynamic analysis, some of the tools like MobSF and Libreda++, and so on. Most of these app-related analyses were done in two different platforms. So one on the actual smartphones, and then actually on the emulated environment as well. Most of these tools had limitations. That's why we had to put in human efforts to kind of analyze the service provider apps. Okay, so going on to discuss about the findings. So like I said, RO1 focused on user-related data. So we kind of look at it overall, there were three different categories of data that was being collected, at least by these e-scooter rental applications. So the first type of data was location data. So location data typically could just be GPS coordinates, but at least in e-scooter rental applications, we saw that location data was collected from multiple sources, not only from GPS coordinates, but also from other sources like cellular network and Wi-Fi identifiers and so on. So from a cellular network perspective, it's probably the location of the closest cell tower, and from Wi-Fi, they use your MAC address of the routers to essentially identify a relative position of your of you or the user. Another type of data that we actually saw that was being collected was identity data. So this identity data could be anything related to the physical identity of the user or the virtual identity of the user. So example of a physical identity would be something like a photograph of you, probably wearing a helmet or parking the scooter, and the virtual identity would be like information about you on social media and so on. So this information was either collected directly from the user during sign up, where the user had to enter the details, or like indirectly via APIs or the third-party libraries that you had in the app without the user's knowledge. And then the third type of data that was being collected was the device-related data. So you had like device either identifiers related to the data, device, or data that's actually stored in the device, like files, like SQL files and so those kind of aspects. So how frequently the data was being collected varied across different of these data types. So you had the location data, which was the most frequently collected data, as frequently as every 15 to 20 minutes. And most of the time, this location data was collected in the background. And another type of data was identity data. It was only collected once, mostly either during sign up or sometimes occasionally you would have to give your data just for verification purposes. Another type of data, which was the second most frequently collected data, was the device-related data. So this data was actually collected whether the app was in use or not, whether you had the app open or not in the background or not. So some of at least 1/5 of the service apps had collected device-related identifiers and shared with third parties, even when the app was not in use, as long as you had the app installed. So this data was being collected and shared. Looking into the data storage practices related to these e-scooter apps, we saw that more than 70% of these applications had both read and write access to external storage, but not all of them had used it. Among the apps that we analyzed, almost 3/4 of the apps had stored some information, either information related to the user, device, or service in clear text format, which is actually a vulnerability. This was mostly identified in the third-party library code base rather than the code base. Another thing that we also analyzed was third parties. So we identified third parties using two approaches. One is based on the presence of SDKs in the application, which was using tools like Androgar and Librera during static analysis. And another way that we used to identify third parties was using the domains with which it shared data or contacted during runtime analysis. So if you kind of look at it, most of the frequently accessed domains or most of the frequently used third-party SDKs were mostly related to data analytics and marketing-related libraries. And the most frequently sent data was device-related data, like either in a raw or combined format. When we looked into the privacy policies, at least what type of information these privacy policies had. At a high level, they had information about what data they collected, either very specifically or in a generic format, and also about third parties. What we also found that not all the policies had do not mention about the data did not have information about the data that they do not collect. So essentially, they did not have any do not collect phrases. Another thing is that we observed is that not all information about the third parties were very specific. For example, out on average, we saw that across all the apps, you had at least 8 third-party SDKs that we identified during the analysis, but only the identities of 2 third parties were revealed in these privacy policies on average. And moreover, they did not have, most of the policies do not have any links or any detailed information about how these third parties handle data, like whether these third parties shared them with other third parties or how long they had kept data that was shared to them and so on. Luckily, there were some moderately popular apps which kind of gave you specific details about what data was actually collected and when it was collected and from who it was collected and to whom it will be shared and for what purposes it was going to be shared with. Also, when we tried to look into how similar these privacy policies were, we saw that the privacy policies had at least most of the content overlap with respect to the data types that are being collected, also with respect to the information related to the third parties, and most importantly, the statements regarding how they handle data or how they use data. The most significant overlap that we saw was in all related services. For example, BIRD and CERC had like 99.8% overlap just because later on we saw that BIRD had acquired CERC, so they had essentially had the same privacy policies with just like a few terms swapped. So another thing that we analyzed was how readable these privacy policies were to different people with different educational backgrounds. So you kind of look at it, if you the least popular apps, almost all least popular apps did not have policies within the recommended readability metric. So what this means is that the policies either had ambiguous sentences or very lengthy sentences or had like technical jargon, which is not really in the commonly used vocabulary. So on the brighter side, comparatively, you can see that at least half of the most popular apps had policies within the recommended range. All that means is that these policies are essentially understandable by users even with limited technical comprehension or even limited English language comprehension. The setbacks that we kind of okay, so another thing, the major issue with these privacy policies is that they had a lot of escape phrases in a sense which gave them a loophole to an autonomy over the data types that they collected. For example, they had like a lot of policies had generic description of what type of data was being shared with third parties. Like for example, they said we may share information about you with third parties for certain purposes, but what is this information about you? We're not really sure. And then also less than 1/10 of the services do not specify like they specify they do not collect this information. Essentially, what it means is like not a lot of policies tell that they do not collect certain information, so which makes it difficult to identify policy violations in this case, especially given the lack of information about the frequency, type, and density of data that's being collected and shared with the third parties. So we kind of looked into the updates or how the apps evolved over time. We noticed that somewhere near the GDPR and CCPA introductions, most of the privacy policy changes happened around that time, and the privacy policy changes were made to represent the provisions that were introduced in these particular laws. Another thing that we actually looked into was the vulnerabilities of the applications over time. So the most found vulnerabilities were like almost more than 85% of these services had third-party libraries which were associated with either insecure data storage vulnerabilities or they kind of did not use sufficient cryptographic primitives. Essentially, they had information in clear text format and so on. Luckily, a fraction of the most popular apps had taken care of these vulnerabilities in the later versions. So that's a good aspect. And the last thing that we looked into from the evolution perspective was whether the policies or the services informed users about the data-related provisions that were available in the data privacy laws and regulations in that particular area or not. So one of the changes was related to notifying users about policy changes or not. Only 32% of the services mentioned that okay they would notify users when they change their privacy policy or not. Whereas another thing that was also there in the provision was related to access and deletion of your data, whether users can access their own data or delete their own data. This information was also present in privacy policies by almost 3/4 of the application services, so which is also a good thing. The only thing that we don't know about is regarding the notification regarding data breaches, which was not available in most of the privacy policies, at least at the time of the analysis. So to sum it up, a lot of entities are affected by using e-scooter rental services. Like some of the users are affected, users like loyal users who have been using the service since 2017. And then also there's a lot of data that is being collected also can be used to infer several aspects about the users. So to conclude, we comprehensively analyzed several Android e-scooter rental applications and the privacy policies. Specifically, we looked into their data handling policies and all the third parties associated with them. And also we looked at how these practices evolved over time. So bottom line, if you're choosing to be a user of an e-scooter rental service, you may be at risk of several inference attacks where adversaries can infer your identity, possession, or what you own, and any information regarding your environment. So that'll be it. Thank you, folks. If you have any questions.
Thank you. I see there are a few questions in the audience, so I will now hand the mic to the first question.
Hello, great talk, thank you. My question is about, I think you found some vulnerabilities in this application. Did you try to reach out to the vendors? How did they respond?
No, not yet.
Thank you. Are there more questions in the audience? Yes, there are. But one more thing, you can also ask questions in our live stream. So on YouTube, there is a chat next to the live stream. So when you have questions you are watching online, you may also ask a question there. But now, next question from the audience.
So you said that they often don't specify which data they are collecting.
Yes.
Isn't this not illegal? So I think it's not complying with GDPR, and it's also not complying with the Google Play Store policies, which explicitly require to state this.
So, so they give you a general idea of what kind of information. For example, they say some policies say we can collect health information about you. This health information could be anything under the sun. So that's the loophole I was trying to say, talk about. If you kind of look at it from the data privacy law perspective, they do give you what kind of information they're providing. From a violation perspective, you need to know the exact data point which is associated with it. So that's why I said it was kind of difficult to actually know whether they violated.
Yeah, so legally they are like making it as
Yeah,
vague
that's like
as
escape
possible.
clauses. That's
Yeah.
why I mentioned escape clauses.
Yeah,
Yes.
okay,
Yeah.
thanks.
Thank you. Are there more questions? No, then there's actually one last thing I would like to know. As we know, we submit a paper to a conference, then it gets reviewed, then you prepare the camera-ready version, and then after a while there's actually a conference. That's what we are doing now. But since you submitted the paper, did something change? So are you still observing that? Do you know whether some new operators appeared or whether some old operators changed their app, changed their policies, reacted to your research?
Yes. At least 15 to 16 service providers have gone out of business. Like, for example, Blue Duck is like not operating anymore. And most of the other services, I'm not exactly sure about the number. They've been taken over by other big companies like Bird, Lime, and so on. So they've acquired those smaller service providers in certain areas. Most important thing is regarding the privacy policies. So just after the CCPA, like at least 3 or 4 months after the CCPA was introduced, most of the privacy policies have more specific information about what kind of data they're starting to collect. But still, it's not very specific enough to kind of know whether they're actually violating certain laws or not.
Great. By the way, when smaller company gets bought by a big one, could you observe what happens? Do they just kill the smaller app?
Yeah, they do not mention that, what they do with the data that they acquired from the previous service provider. So that's also something that we're not aware. At least they don't mention in the privacy policies.
But then the smaller app just gets killed, or do you see kind of mergers?
No. They just operate under the same name. It's just, yeah.
Okay, thanks a lot.
Yep,
Then applause for the speaker again. And we have our next presenter, that's Frank. Please come to the stage. And while Frank is setting things up, I can briefly summarize who he is. It's a paper that started at the Florida International University as a summer research intern. So that is a project that was simply a summer research project, but now he is actually at Georgia Tech. So I think at the paper, you can still see Florida National University, but now he moved on and he is now with Georgia Tech. Yes.
Yes.
So now the stage is all yours. And yeah, we are excited about your presentation.
So my work was to present the first look at code obfuscation for WebAssembly. Our primary motivation for the study was to provide a preliminary evaluation of WebAssembly obfuscation and evaluate how effective that obfuscation was from two different perspectives that are shown there, dissimilarity and detectability. I'll go more in depth on those later on. For those of you who don't know, WebAssembly is a compilation target for high-level languages within browsers that facilitates the creation of high-performance web applications. It does this using a low-level bytecode running in browsers that is not really similar to assembly, but it is a machine code that gets eventually compiled within the browser to binary. And it's extremely efficient since it is performance-oriented, and it is commonly used in IoT and edge computing, and because of its performance, it is very effective on mobile devices and other hardware-constrained devices. Because of that performance orientation of WebAssembly, one of its main uses is cryptojacking malware. So as you can see on the right, the majority of WebAssembly instances found in the wild in the top million Alexa websites are malicious instances of WebAssembly. Because WebAssembly has access to the entire JavaScript context and it purely runs within the browser, not creating any system calls or anything similar to that, it means that any malware can run without being detected by a native antivirus. So because of the platform independence, meaning it can run on iOS, Android on its own as its own operating system or within browsers, it has also allowed malware authors to target multiple different devices at once without having to tailor malware for those specific devices. On the other hand, obfuscation there's two main forms of obfuscation. The first is control flow obfuscation, which is done by modifying the control flow graph of a program. It is effective, it is usually commonly applied at the highest level of program, being the source code, so say C, C++, or Rust in the context of WebAssembly. And then as the program is compiled, those control flow obfuscations tend to follow through to the binary level. These forms of obfuscation can be resistant to both static and dynamic analyses, which are the common way to analyze a program. Data obfuscation, on the other hand, is an attempt to make data harder to decipher. Often it is more effective at the higher level. Say, if you have a variable, you can just, a very primitive data obfuscation would be to just change the name of the variable. But as you compile and get to the binary level, those obfuscations tend to be abstracted away. But sometimes control flow obfuscations can result in data obfuscations or vice versa. Here's an example of the original control flow of a program and the obfuscated one underneath using a variety of different obfuscation techniques. Traditionally, a program is obfuscated using an obfuscator, which is a program that takes in a source code or a piece of unobfuscated code and will apply obfuscations to it in an automated manner that it would not be realistic for a human to do so. So our approach for obfuscating WebAssembly and measuring it started with the threat, right? A malware author targeting the WebAssembly platform can hide their code in one of two methods using obfuscation. The first is to use an existing high-level obfuscator. We think this is the most realistic because, one, obfuscators that are made for high-level languages like C and C++ tend to be more complex and be able to apply obfuscation techniques that aren't really primitive. And second, they're easily and readily available. Some of them are free, some of them are paid for, but obfuscators like Stunix and like Tigris are pretty commonly and well-known, or commonly used and well-known. The second option is the more unrealistic one, which is to create a low-level obfuscator for the WebAssembly language itself. WebAssembly is a language of its own. It is a machine code that runs on a stack machine, and it's not really similar to any other existing language, so no obfuscation technique can be applied to it. Many people think obfuscation techniques that have been applied to traditional assembly or x86 assembly can be translated to WebAssembly, but this isn't the truth because assembly or traditional forms of assembly run on a register machine, which means gives you access to things like jumping to the function table and things like that, or jumping to other sections of code. These things don't exist in a stack machine, meaning that we can't adapt those methods to use for WebAssembly. We also think it's unrealistic for a malware author to create a novel obfuscator for the sole purpose of obfuscating their malware when they can do so with their source code. With their source code that they'd be compiling from. So for that reason, we chose to start with the C language because that is C and C++ are two most commonly used languages for WebAssembly, source languages. And we used the Tigris obfuscator. We chose Tigris as the obfuscator of choice because of its rigorous testing in the literature and its availability of various obfuscation techniques. We chose the 7 techniques listed there based off of their appearances in the literature and how, for example, opaque predicates has been rigorously tested and it tends to be the standard obfuscation techniques most studies would apply. We also wanted to measure if obfuscating at the highest level at C, C++, Rust, etc., can carry through to the WebAssembly machine code or the binary level. So by applying our obfuscation at the highest level, it allowed us access to complex obfuscation techniques, as well as our ability to measure what effect the compilation process has on these WebAssembly programs. We did this by using a data set consisting of C source code WASM applications. These are applications that are written specifically for WebAssembly, but the source language is written in C. And then we split the data set into 2 parts. The original unobfuscated programs in the data set are compiled as they normally would. The compilation process for WebAssembly is it starts with the source code. It goes through a compiler called mscript, you can use multiple compilers, but the compiler of choice is mscriptin for most WebAssembly development, which results in a WASM module. This WASM module can then be inserted into a web page and instantiated in the browser with JavaScript, which triggers the second compilation process within the browser, which is a 2-tier compilation process that changes depending on the context of, is it running on mobile, is it running on iOS, is it running on Android, etc. On the other hand, on the other side of the pipeline, we inserted our unobfuscated source code into an obfuscator, applied the obfuscation techniques, leaving us with 7 new samples. Each of these samples is an obfuscated version of the original code, corresponding code in the data set, and then it went through the same process below. It went through the mscript and compiler, we were given a WASM module, and then it was inserted into a web page, instantiated, and compiled. At these 2 different stages, the WASM module stage and the WASM binary stage, we compared each of the 7 obfuscated WebAssembly programs to their original unobfuscated counterpart in an attempt to analyze it and see what effect the obfuscation had and how the compilation process affects the obfuscation. There's 2 ways that we evaluated the performance of obfuscation. The first was, before we get there, first let me go over what the data set looked like. This is the breakdown of our data set. These were the main categories of WebAssembly programs. Almost all of them can fit under either games, libraries, applications, or cryptojacking malware. We had a small data set, as you can see, but the reason for that is because we wanted to make sure we had a realistic data set. We could have just chosen any C program and obfuscated it, but instead we wanted programs that were made for WebAssembly, used in the wild, and could be effectively obfuscated using our obfuscator. All of the samples that we chose also run on mobile devices without any performance impact or performance loss. We could have chosen applications that could only run natively on Windows or on a browser on a desktop, but oftentimes there can be programs made for WebAssembly that can't run on mobile devices. But since cryptojacking often targets mobile devices as well, we wanted to make sure that we included programs that are compatible with running on mobile devices. Our cryptojacking samples, as you can see, we have a relatively small cryptojacking set. It's only 2 samples. This was limited for 2 reasons. The first is because many cryptojacking malwares their source code is written in C++. That's if their source code is released. We need the source code to be able to obfuscate it. Oftentimes, you can pull just the WASM module, but we can't really do much with that. The second is that for samples that were written in C, sometimes they use libraries that weren't compatible with our Tigris obfuscator. Of course, you can make your own obfuscator that would be able to be compatible with those libraries, but that was out of the scope for this study, as it was just a preliminary evaluation of the effect that obfuscation can have. Once our data set was obfuscated, you have the breakdown here. This is including for every original sample we had 7 new samples, each of them being individually obfuscated. Each of the original 15 programs that we had obfuscated 7 different ways, which led us to a total data set of 120 programs. The first way that we evaluated obfuscation was through similarity or dissimilarity. Because the end goal of an obfuscation is to produce a dissimilar product or a dissimilar program, we chose to measure the similarity between our unobfuscated and obfuscated programs. There are many different ways to do so, many different metrics that you could use to measure. Historically, in obfuscation literature, there were 3 metrics that people used. These are 2 common ones. The first is complexity metrics, like McCabe or McCabe cyclomatic complexity number or things like that. These were originally measures of program structuredness and used variables like amount of lines of code and amount of variables used and things like that. We don't think that's a very reliable metric. It's not very reliable in terms of different languages or different minor edits in code can result in a very different cyclomatic number. It also can't be applied to low-level languages like machine code or binary because it is reliant on things like having high-level abstract ideas of functions, variables, etc. It's an outdated metric that hasn't been used in a while. The other common metric is cost metrics, which are just space and time overheads. This is very hard to use for WebAssembly since WebAssembly is very dependent on the hardware it's being run on. Using cost, like space or performance as a metric for comparing a mobile device's cryptojack malware versus a native like desktop malware isn't really realistic since platform independence is something that WebAssembly prides itself on. It also doesn't reveal any meaningful insights. There's no way to know how effective the obfuscation was. For all I know, it could have just made the program slower. It's not a reliable method either. So we chose to go with the third most common method, which is similarity. Cosine similarity is the similarity metric that we chose to use. It is a good way to measure how similar or dissimilar machine code is. And we did so using cosine. The reason we use cosine similarity is so that we could use n-gram analysis. We think cosine similarity is the best form of similarity metric that we can use because, say, for example, Euclidean distance. And trying to take the measure of Euclidean distance between an obfuscated and unobfuscated program, say that just the program, the obfuscation added 20 lines of code at the bottom of the unobfuscated program. The Euclidean distance would be high, but that program is still similar because if I put 20 print statements at the bottom of a whole program, the program is still functionally doing the same thing. It might just print something 20 times. But cosine similarity would allow us to offset that, allow us to see, even including length as a metric, it would allow us to be able to see how similar the program itself is, regardless of things like that. We also use CF-IDF vectors for our n-grams to offset any difference in length or things like that. And we use n-grams because since WebAssembly runs in a stack machine, it allows us to see and measure the line or operation that came before it or after it. Because WebAssembly is just a series of pop and push operations, the order in which those operations are executed matters a lot. It's extremely important. So that's why n-gram analysis is vital to be able to measure WebAssembly obfuscation. These are the results of the similarity. We took the average in each category of program, and to the left, we have listed each obfuscation technique. For each bar, lower is better. This is a measure of similarity. So the closer it is to 0, the more dissimilar it is. As you can see, there isn't any real pattern to the data besides that alias disruption is effective regardless of the category of program. But the one thing that is noticeable is that with the exception of taint disruption for applications, almost every single obfuscation technique resulted in the binaries having a cosine similarity of less than 0.5. 0.5 tends to be the threshold for what is similar and dissimilar, meaning that we can categorize every obfuscation technique, again, except for taint disruption, as producing dissimilar binaries. This is just the graph for binaries. So the implications of that are that high-level obfuscation techniques directly obfuscate the WASM binaries. There is a correlation, and it is a direct result of the obfuscation that we applied at the highest level, in this case, the C level. The majority of our obfuscation techniques were successful with similarity being less than 0.5, and there is no one best technique. If you look, it depends on the category of program. While taint disruption might be the best for libraries, it obviously is not the best for applications. The obfuscation and the effectiveness of the obfuscation is reliant on what type of program is being obfuscated and the content of that program, which means there is no one golden bullet for obfuscating WebAssembly. But while we've arrived at the conclusion that obfuscation can result in dissimilar machine code and binaries, that doesn't mean we can conclude that the obfuscation was successful. A successful obfuscation, in the context of, say, malware, would be that the obfuscated program is not caught by an antivirus. So we tested exactly that. We tested the detectability of those cryptojacking samples. Traditionally, and even in the context of WebAssembly, there are two ways to detect and analyze WebAssembly programs. The first is through static analysis, no surprise. It analyzes the program's file. These forms of analysis tend to be more lightweight because it's simply checking the file. This is also the most popular option for cryptojacking detection because oftentimes these have to be run within a browser without having a large performance impact. And this can take many forms, including learning-based methods, string matching, fuzzy hashing, etc. This is also, these defense mechanisms tend to be written for mobile devices as well, so they tend to be very efficient. On the other hand, dynamic analysis requires running the program, requires computation, and creates a performance overhead that isn't realistic for cryptojacking detection methods to have on hardware-constrained devices and mobile devices. So common dynamic analyses like taint tracking and memory access tracing are not realistic to be implemented for mobile devices. And in the literature, while these methods do exist for WebAssembly, they would never be implemented as a method in real time to detect cryptojacking samples. Instead, we use MINOS, which is a deep learning-based static analysis detection method that uses a convolutional neural network to analyze binaries of WebAssembly files and categorize them either as malicious or benign. It analyzes these grayscale images using the pattern shown to the right. This pattern is the standard pattern that binaries of cryptojacking malware use. It is a 98.97% accurate, or 99% accurate, cryptojacking detection method that can and has been run on mobile devices without creating a performance or a significant performance overhead, meaning it is realistic to use in the wild. It was published in NDSS and has been rigorously tested in literature. What we did is we fed all of our samples, all 120 samples, including the unobfuscated and obfuscated, into MINOS. The graph is shown to the right, and while it might be a little hard to tell what's going on, if you notice there are two rows that are in red. That first column is the unobfuscated. MINOS detected our cryptojacking samples when they're unobfuscated and correctly categorized them as malware. But once we obfuscated them, almost every single obfuscation technique bypassed MINOS, meaning all of our cryptojacking malware, with the exception of one technique using flattening on one of our samples, was able to trick a previously 99% successful and accurate cryptojacking detector. Our cryptojacking obfuscation was 93% successful, and then any other of the obfuscated samples, any other sample that was detected as malware was almost always incorrect, creating a 70% false positive rate, which rendered MINOS completely ineffective. This showed us that obfuscation for WASM binaries for malware can be successful in the wild. And even though we only had 2 cryptojacking samples, we think that analysis can be extended to more than just those 2 because they're built on Cryptonite, which is a hashing algorithm that's very commonly used for Monero miners, which is the main type of crypto miner used in the wild. So our benign samples were also being flagged as malicious, which renders learning-based detection systems like MINOS. There's more than just MINOS that uses that similar detection method of analyzing the WASM module or the binaries and categorizing them as benign or malicious. We know for sure that it will render those forms of static analysis ineffective. But we can also conclude that there are other forms of static analysis that the same way, because we're changing what the binaries look like, that they will end up also being ineffective. Our results can be generalized to other cryptojackers, which I already mentioned. Cryptonite is the basis for the majority of cryptojackers found in the wild, and those were the 2 cryptojackers, or the 2 cryptojackers that we used were also built on Cryptonite. Which leads us to some concluding thoughts. Here, our contributions were that we presented the first comparative analysis of multiple obfuscation techniques for WebAssembly across a variety of different WASM-based web applications and mobile applications. This was, again, just a preliminary introduction to what obfuscation can do for WebAssembly. We've also demonstrated how obfuscation can affect how the obfuscation of WASM web applications can affect these static analysis tools like MINOS and their ability to discriminate between benign and malicious web programs. So we presented the first analysis and evaluation of obfuscation for WebAssembly. High-level obfuscation has been proven to be effective in producing dissimilar binaries, and obfuscated WASM malware can bypass status quo detection methods, which poses a significant threat to IoT networking and mobile devices, since it is the first time, or not the first time, but WASM is being used very commonly to create a platform-agnostic virus like cryptojackers that can run regardless of the native operating system. These are references. Thank you for your attention.
Thank you. So, are there questions from the audience? Yes, there's one.
Hi, this is Jiska. Thank you for the talk. I would like to know, have you looked into obfuscation beyond malware, like if a company wants to protect their intellectual property?
So if we go back to here, all of our samples, including the libraries, the games, the applications that we have up top, they were all obfuscated. So we have the similarity results in terms of how dissimilar the categories are listed down here: applications, games, libraries, etc. So looking beyond cryptojackers, we had a more comprehensive data set for things that weren't malicious, for things like applications and games and libraries. We can see the obfuscation is still successful. And then when it comes to, say, trying to reverse engineer it or looking at patterns, you can tell that the obfuscation clearly disrupts the patterns, since it creates a false positive rate where benign programs, or originally benign programs, are being flagged as malicious. So yeah, it would be pretty effective on even benign programs to deter software reverse engineering. Yeah.
Thank you.
Thank you. Excellent talk. Forgive me if I missed this. My understanding is that you took the obfuscation in the original source code.
Yes.
And then you saw the effects in the WASM code.
Yes.
Did you see if you had similar effects if you would have compiled it to native directly? So do these, it's basically, is this an artifact of it's a really good obfuscator, or is this something specific to the implications of using WASM on top of that?
So there have been previous studies in the past that analyzed the effect of our obfuscator in specific on native binaries. And while it was successful, what we wanted to measure was the difference between the WASM compilation process in the context of its browser compilation process. While we can obviously check the WASM module that's included in a web page, we can analyze the machine code there. Because of the two-tier compilation process that every WASM program uniquely goes through, we wanted to see, can the obfuscation carry through that? And it's also because of those pre-existing studies of using native binaries to measure compilation, or to measure obfuscation, we wanted to see, since WebAssembly doesn't run like how a native program would in a registered machine during its compilation process using traditional assembly or something adjacent to it, we want to see the effect that using a stack machine, which is what WebAssembly uses, had on those obfuscation techniques. Because a lot of them might be optimized away or be gone completely when using a stack machine.
So was it more, less, or equal?
It was roughly equal.
Roughly equal?
Yeah.
Okay.
Yeah, great talk. Just a quick, again, maybe a clarification question. You showed results for similarity in machine code.
Yes.
Did you study the similarity in terms of control flow? So, for the...
So like recreating the control flow graph from, so there are no tools readily available to pick apart, say, the machine code or the WASM module to be able to recreate a control flow graph from that code. If those tools were available to us, then we would have done that. But to create that tool would be out of the scope of just what is really just a preliminary evaluation of the performance and the effect that obfuscation has on WebAssembly.
But that would give better insight on why.
Yes. So based off of the results that we have, we think that if we were to recreate the control flow graph based off of the WASM modules or the binaries that we measured with the similarity listed here, the control flow graph would look extremely different than the unobfuscated program.
Because there's an intuition right now.
Yeah. So if there is a program to reverse engineer WASM modules because they are just machine code, and then recreate that control flow graph.
But there are tools that also use a control flow graph and the differences, the minor differences to kind of still detect.
Yeah. So a lot of those tools that we saw they were forms of dynamic analysis that would be not realistic for us to use as a metric like this when we have other metrics like detectability. That would be a much more realistic metric to use practically for software developers. and a lot of the ones that would, traditional ones that take in a file and then just produce the visualized control graph from it. Well, we could do that with the source code, and it would obviously produce a radically different control flow graph. There is no, because WASM is such a new technology and it's a new language, there aren't a lot of those reverse engineering tools that are available yet for us to be able to apply to our WASM machine code. There are those that can be used for the binaries because the binaries are just binary, but those tend not to be the most reliable because depending on the platform that our WASM machine code is compiled on, whether it be mobile or desktop, it can produce radically different binaries.
Thank you.
Thanks a lot. So, thank you a lot for your presentation. Applause to the speaker again. And I am now happy to announce Alexander Heinrich, who is from Technische Universität Darmstadt in Germany, from the CIMO group over there. It's a great university. I know that because I studied there, I graduated there. Great place to work and live. And yeah, he is a PhD student there, and he did a joint project together with Niklas, who is also here on stage. Niklas, where are you? Here, over there. So when you have questions about the paper, you can ask him, or you can also ask Niklas, who's also on stage, and I see many other people from CMWare as well. Now, the stage is all yours, and go ahead with your presentation.
Thank you. Yes, I'm Alexander, and I'm here to talk to you today about a thing that has been covered a lot in the media, and that's AirTags and how they are maliciously used to stalk people and track people. So at first, I want to start out and explain what is an AirTag and how does it work. So AirTags are this coin-sized small things from Apple, and they're super cool because you can attach them to everything you have. When you're putting stuff away and you don't find it often again, then an AirTag is a nice thing because you can use even ultra-wideband to find where it is, get distance measurements, let it ring. So it's quite nice. Then there's a second cool feature. When you put it on something and lose it somewhere in the city, like this Alan did here, he lost everything all over the city. You can get actual location updates in almost real time where those things are. So if you left something on the bus, you see it's still driving with the bus, or you can see, okay, where do I need to go to pick it up? This is nice, but there shouldn't be anything wrong with that. Or, okay, apparently, then one person got tracked. There's an Instagram model, and she got an AirTag into her code, and this led to the thing that after like 4 hours or something, she got a notification from her iPhone that she's being tracked, and she found this device in her code. And then she doesn't know who put it in there and why is it there. So in the end, was one of the first persons who were victim to this. But it turns out there are more people that are having this issue. So people are tracking other people with an AirTag, not their things. And apparently they're also stealing cars with it. So they're putting an AirTag on a car, which they think that looks nice, and then they track where this car is being parked normally. Then they go there at night and tow away the car or use other things like techniques that have been shown here at WiSec to steal cars. Yeah, so there are problems, but there are protection mechanisms by Apple. So for example, if you have an AirTag and you disconnect it from the iPhone, at some point it will start making a sound. It's like this. The sound is not super loud, even though it was amplified here, but it's audible. And if you have it in your bag, then at some point you will get to know. So that's a good protection mechanism, but there are people who were like smart enough to disable the sound because just the speaker in the small AirTag, you can cut it off and then you can disable the sound. And didn't took them long. So if you check here, this video has been posted on May 2nd and the AirTag was released in April 30. So it's like 2 days until there was a video how to disable the sound on an AirTag. So yeah, that's not the most reliable protection. So we have something nice in iOS actually. So if you have an iPhone, then you walk around and the iPhone will recognize that there's an AirTag following you, and you will get a notification when you tap on it. Then you get all these details, where has it been seen, and all the locations it traveled with you. You can even play a sound if it's not disabled. And it's a reliable feature and it works. But what about Android? So people in Android were complaining from the beginning. So Apple published an app in December 2021. And this app is not as cool as the iPhone thing, but you can tap a scan button and then it scans, and then you find an AirTag maybe, and then you have to wait 10 minutes, and then you can try playing a sound, and that's it. And there's nothing more that this app can actually do. And it only works with this scan thing. So when you are thinking there's someone tracking you with an AirTag, you have to continuously check everywhere where you go on all the things that you have with the scan feature if there's actually an AirTag trying to track you. But it doesn't have to be like that. So we made AirGuard, and AirGuard is the solution to a problem, or a part of the solution here. Because with AirGuard, after you set it up in the first way, you can put the app away, don't have to think about it anymore, and when there's an AirTag tracking you, you get the notification. As on iOS, you can tap on it, then you get all these cool locations where you have been tracked, so you can see, is this like an actual problem? Someone is tracking me, or was there like someone on the bus with me on a plane? You can also bring it, so you can play the sound, and you get more information as on iOS. You have more details, you can view all locations by different trackers, you can check when was the last time the app has scanned in the background, how often am I getting notified, and when has the last notification happened. So you can always get these statistics to make sure that you're safe, or to help you identify where this tracker might be located. And to explain you how this works, I will quickly explain the Find My network. So this is how the AirTag is able to get the GPS location of it back to your phone. So when you first have an iPhone and you set up an AirTag, or also other trackers which are cooperating with Apple, then they're exchanging some private public keys. So this key exchange happens initially in the setup, and then when this tag gets lost or placed at someone, then it will lose the Bluetooth connection. And then it starts publishing this public key over Bluetooth Low Energy. And other iPhones that are walking around, they recognize that. And they're like, okay, here someone has lost an AirTag. And they use their own GPS location, encrypt it using the public key that the AirTag is sending out. And then they upload it to Apple servers. And there in Apple servers is basically a public database with all these encrypted locations. And when I'm now using my iPhone to check where my person is that I'm currently tracking, then I'm downloading the encrypted location to the iPhone, and it gets locally decrypted because I have the private key on the iPhone. So it's a privacy-friendly system in itself, but it's used for not privacy-friendly things. For AirGuard now, we are using a tracking detection that is running in the background. So we scan for Bluetooth devices, similar as iPhones do it, that are finding AirTags. So, and we use this to save then the MAC address of an AirTag, its device type. So we also can find other devices like a Chipolo tracker or an AirPods, for example. We save that in the database, and also the current location where I am currently, so we can present it to the user later. Then after this scanning is done, we check for all the devices that have been found. Okay, have they been following me for more than 400 meters? Have I seen them at least 3 times through scans? And am they following me for more than 30 minutes? So we scan, or try to scan, every 15 minutes. Android might delay this a bit, depending on the battery settings of your manufacturer. But in the end, when all these 3 things are valid, then you will get a notification, and you can check these locations where this device has been following you. And this gets updated. So even if you don't find it right now and it still follows you, you can go back always and see where what are the trackers following me, and you can see if it actually continued following you. So this is a good thing. And we currently support not just the AirTags, as I just briefly mentioned, we also support the Chipolo tracker, which is a Find My compatible tracker from some third-party developer. We also support AirPods, which have the same feature, and we support OpenHaystack tags, which are self-made AirTags that we created even before the AirTags were available in March last year, just to showcase that things like an AirTag would work. They are based on a system called offline finding that MacBooks and iPhones use when they lose their internet connection. Then they use the same Bluetooth features as an AirTag to be found by other iPhones. And recently, we also added support for Tile, which is really not visible. But yeah, okay, you see there's the Tile logo. Yeah, so they can also be found with AirGuard, and you can be protected. So it's not just against one tracker type. So it's also against tiles. In the app, we have 3 risk levels. So when you're not being tracked at all, then you get a green app. When we detected one tracker that has been following you for no more than 1 day, it turns to orange because, of course, there can be false positives. You cannot be sure if this tracker has been seen on an airplane trip. So now when I was on a plane, I got false notifications because there are people having AirTags in the plane, and then it would change to orange. My app is always red because I carry AirTags around with me that are tracking me for testing and for a continuous amount of time, and then it turns to red. So with one check, you can see what is your current risk, and if there has been no more AirTags found for two weeks, that will go back to green then. One thing that we also introduced rather recently is that manual scan feature. So when you hit the manual scan button, you can scan manually for all the AirTags and other devices that we support around, and you can play a sound immediately. So let's make this not too loud. So it scans now, and then you press the play button, and then it connects to the AirTag and tells him to play a sound so you can find it. Yes. Oh. Yeah, and we evaluated our app against Apple's, and we have some real-world observations I want to show you. So Apple's tracking detection is integrated in iOS. In our paper, you can also find out how we reverse engineered it and how it actually works. But here I want to show you how we evaluated it against our app. So we chose 3 scenarios based on news articles we found. So there was this thing I already told you. There was a woman being tracked by an AirTag in her coat. We have it in a backpack, which is a common thing because you can hide things quite well there if they have a couple of pockets. And we put it on the car in the fuel cap because that seems to be a position where thieves want to place it. And for all these 3 scenarios, we also use 3 types of trackers. So we used an AirTag, we used a third-party one from Chipolo, and we used an OpenHaystack self-made tracker. So we can see here in this graph, that's the time it took until every tracking detection system sent a notification. So AirGuard, for example, for the first case with the code, that's blue, was taking about 30 minutes to detect that there's trackers around traveling with me, and then send out a notification. There was the same case for the backpack, and the iPhone took always longer, but we can see in the logs of the iPhone that it actually detects these trackers way earlier than this first one was 1.5 hours, and the second one was 4 hours. But Apple decided that they won't notify people if they're not returning home with this tracking device. So the first one is after 1.5 hours, we were like, okay, maybe we're not getting a notification on the iPhone, so we returned home. And then when we returned home, the iPhone knew, okay, this person is now home, does another scan, sees if the tracker is still there, and you get a notification. For the 4 hours, we were testing, okay, with the backpack, we just stay away until we get a notification, and it takes about 4 hours, you will get this notification. It works, but it's delayed. For the car version on the AirGuard, it worked, but here the scenario is a bit different because we were not driving with the car for hours, because that's obvious that it will be detected. We were using like a normal way how you use a car. You take the car, drive somewhere like 20 minutes, then you are there for some time, then you drive back. And this time in between was more like 2.5, 3 hours, and then AirGuard detected it on the way there 2 times and on the way back 1 time, and it saw that the app saw that these devices are traveling with us. And the iPhone, for some reason, does not detect this option because our guess is that it just takes into account all devices that have been found on the day. It just clears the database at some point and then says, okay, now we start scanning from scratch again. And then, okay, there's a new tracker, but it's not following us for a long time, so there's no notification coming in. So be aware, sometimes you won't get a notification with your iPhone when you're driving with the car. It can work, but it doesn't work all the time. Yes, then we want to briefly talk about the self-made trackers, because the iPhone does not detect them at all. And the problem here is that the self-made trackers, those have been made even before the AirTags were announced, and their Bluetooth advertisements are like 1 bit different from what an AirTag is sending. So there's like 1 bit. If you change that, then you will be notified because the iPhone thinks it's an AirTag. But if it's not thinking it's an AirTag, it's actively ignoring these tracking advertisements that are sent out because it thinks it's an iPhone or a MacBook. And that's an issue because they're actually very easy to detect because they never change their MAC address, they never change their public key. It's always the same. AirTags change them like once a day, but in self-made trackers, at least the ones that are out there now and that we have presented at WiSec last year, they just are one public key all the time. So it's very easy to detect them. They will follow you for a long time, so it's not a problem, but Apple actively ignores them, and we also recently got to them and told them about it again, because there were researchers that found out about this previously, and we told them again, but so far we don't know if they want to change this or not, but it's possible. Now I want to go to our real-world observations. So when you download our app, you can voluntarily participate in our study. And this is then only sharing anonymous data with us. So when you agree, then, for example, all the notifications that will be received are shared with us, all Bluetooth scans that are done, and all the advertisements that will be found are shared with us, but in an anonymous way, so we don't get any MAC addresses, we don't get any locations where they have been found. We only get basically the time, RSSI values, and the devices which they are linked to. And from this data, we are able to tell certain things. For example, the distribution of devices that we can see that are not of all devices that we have found with the app from our more than 38,000 participants are 5% AirTags only and 95% Apple devices. And this is to be expected because, as we know from Jiska's talk, an iPhone changes this public key and identity every 15 minutes. So the iPhone will always look like a new device to the AirGuard app every 15 minutes. And that's what we want because we don't want to give like so many false notifications about iPhones that are falling. And that's also what Apple is doing. So it's to be expected that there are much more Apple devices than AirTags. The AirTags change only once a day. But when we look at devices that actually send out a notification or are causing a notification, we can see that there's more AirTags in there, but there's still, in this period that we analyzed, a lot of Apple devices. And this led to the conclusion for us that Apple is, I mean, they don't document how they're doing it, but they're not always keeping this 15-minute time range they are actually supposed to keep. In this measurements for the LPM paper of Jiska, we saw that sometimes one key stays in longer. And from our database, we can tell that the Apple devices sometimes keep the same key for about 90 minutes to 1 hour, like 1 hour to 90 minutes, even though all previous research that we have done we saw that the key is changing every 15 minutes. So there are like things that are weird here, but we now changed this that an Apple device won't trigger notification for after 30 minutes. It's just delayed a bit. And so therefore we will still detect the open haystack tag, but also trigger less false positives. To see that what we think shows that the app actually works is that when we look at the RSSI values, that AirTags and other devices that trigger the notification are normally a bit closer. So we have a lower RSSI than devices that don't trigger notification. And also we can see that we get reviews on Google Play that are showing that people are that use this app are actually finding trackers which were used to attack them. So here I have just some free reviews, and 2 people found them in their car, and 1 person found that someone was tracking the location with an AirTag in their bag. So this is great for us because then our research is actually used by actual people, and those persons are also gaining privacy from that, and they can control who knows their location. One thing that users can also do is sending feedback. So when they get a notification, they can say, okay, I want to say in one of these 4 categories, this device has been placed when they found it, and they reported to us, 1 person reported to us it was in their clothes, 4 reported it was in a backpack or a bag, 1 was attached on a bike, and 8 people were finding a tracker in the car. So is this now actually the solution to this problem that Apple is not really caring about? From my perspective, I would say not, because we have 120,000 users, so it's a cool amount of users that are actually being protected now, but it's billions of Android devices which are not being protected. So what we think is an OS level integration is the best solution here, and that shouldn't be just to protect against AirTags, but also to protect against other trackers like the Samsung Smart Tags and Tile devices. And there are rumors that Google is working on that, but I don't know too much about it. And the same thing should happen on iOS because they protect against AirTags because they know about the issue, but they do not protect against other trackers. And what I also think is really important is that they would have minimum standards because, as we have seen, the AirTag is making the sound, but if I use the Samsung Smart Tag to track someone, it's never making a sound after a time to say, hey, I'm here, and maybe you should look out for it. Also, tiles don't make a sound, so that would be great if all just agree on some certain standards. So what are we doing next? We want to enhance our scanning and detection technique because, as I said, Apple devices are not detected as trackers normally because we expect that they change their identifier they're sending out every 15 minutes. But that's also a problem because you can modify a self-made tracker that it also changes the identifier every 15 minutes. And then you're building a tracker that is not detectable by AirGuard and also not detectable by the iOS tracking detection. And we are now looking into making this possible to detect trackers that are trying to circumvent being detected. Obviously, this is not the normal attacker that does this. Then we also want to integrate smart tags, but smart tags actually do this on their own. So they always change the identifier and MAC address every 15 minutes. So it's exactly this enhanced detection we also need to detect smart tags. We are also doing a survey now on our users and other people that are victims to this and how to identify how we can help them better and what their problems are, what the general stalker looks like, and how protection mechanisms can be enhanced. And at last, we are also working on an iOS version, which is not detecting AirTags, but Samsung Smart Tags and Tiles. Yes, and this finishes my presentation. And if you have any questions, I'm happy to answer them.
Thank you. So, are there any questions from the audience? Yes, there are. So thank you for your talk. And here is our first question.
Thank you for this awesome talk, and I think you've really helped us understand what's going on under the hood with these things. And it sounded like there's more than just these AirTags. There's the AirPods as well have these identifiers, and these identifiers are maybe not changing as frequently as you might want. So I'm curious if you thought about how someone might use your application to tail someone in a city or in a busy area.
Use our application to tell if someone is...
Tail you, right? Follow. You're maybe 30 feet ahead of me, and you got AirPods, and I can just sort of follow you, and I know where you're going, or on a subway.
Well, yes, I guess you could do that, but since if you use the manual scan, for example...
I'm not saying it's not your problem.
Yeah.
I mean, Apple did this, right?
Yeah. So yeah, I agree. Yeah, I think you could do this because if you use the manual scan feature in the app, then you can scan manually. So you see that there's an AirPods wandering around in front of me, and you see also the MAC address. So that shouldn't change so often on the AirPods. But the AirPods are really behaving super weird with Find My. So for example, you can also sometimes play a sound on them, but not always. And then I think they also try to keep a connection with the iPhone. So if someone uses AirPods and they probably have an iPhone and they're playing music through it, then it might be that Find Bots. But on the AirPods, the Find My part of the firmware doesn't really work that well, at least from my personal experience. I also get notified about my AirPods trying to track me all the time. So I'm not sure it could work, but I'm not sure if it will work. Yeah.
Thank you. I think there was a second question in the room, right?
Yeah, here.
One. Oh, we have more. Okay, let's get over here first.
Thank you. Just one clarification first. So if you have an iPhone and someone else's AirTag is nearby, you can ping that AirTag that's not yours?
Yes, but not if the iPhone is connected with the AirTag. So normally the iPhone keeps the active Bluetooth low energy connection with all AirTags that it has.
Okay, so my question, what about the original users? Like what if I want to put an AirTag on my car to protect it, if someone stole it to track it, and now your app just tell them, oh, this is the AirTag, just get rid of it.
Yeah, the AirTag is not made for theft protection. So it's for losing your things. Yes, it would work, but also the AirTag makes a sound, so maybe the person would hear it anyways. And also if the person has an iPhone, it would also be notified. So I think the value here to protect other people is higher than protect the belongings of people, even though it might be hurtful to lose your car if it's stolen. I see that, or your bike and everything that belongs to you. But tracking people is, I think, a bigger problem.
Thank you.
Thanks. And we have another question from the room.
Hey, awesome talk. I was wondering now if I travel with someone in a train and they happen to have an AirTag with them. So did I understand that correctly, that as long as they are nearby, it won't accidentally trigger that detection?
Yes, exactly. Yeah.
Okay.
So we are really just, the AirTags have two different advertisement formats, and one says, okay, I'm connected to an iPhone, and we ignore this. And one says, okay, I'm in this tracking mode. And as long as it's connected to an iPhone, it's also not trackable. So other iPhones cannot forward the location because parts of the public key are missing.
Okay, right. Thanks for the clarification.
Thank you. And there's actually a last thing I would like to know. You mentioned that Apple specifically looks at, well, AirTags that are with you when you drive your car home, right?
Yeah.
So how does that work when you do not park your car in front of your house? So for example, we are now in the US, so basically next to every house there is a parking spot for a car. But depending on where you live in Darmstadt, you can be lucky when you can park your car less than 10 minutes walking distance away from your home, and then usually you walk the last kilometer back home because there is simply no free parking spot on the street. So how does Apple know whether you are now returning home with your car.
Yeah, so I think this car detection is an actual problem because in our test it also didn't work. And Apple will notify you as long as the tag stays with you. So if you are in this car for a really long time, then you will get a notification if you are around the car. But as you said, it is very likely that this wouldn't trigger a warning from an iPhone.
Assuming that the tag is attached to the car, but not to my clothes.
Yeah. So if you leave it on the car, you have to go away, then the iPhone scans again and doesn't find the tag again, then thinks, okay, it must have been someone else. And they really don't want to give you false positives notifications. So they are a problem. I see that false positives can be hurtful, but it's also a thing about how you can communicate it. And I think this locations to show you where this device has been used for tracking helps you a lot for the people itself to know if it's a false positive or not. So, yeah.
Thank you. Okay, that concludes the session. Thank you for all speakers. And now I give the microphone back to our chair. But one last thing, please, a final applause for our final speaker of the session. Thank you.
Great session. Thank you very much, everyone, for staying back until the very end. So this is going to be our last session for today. But don't retire for the day. We still have the award ceremony and a dinner to go today. So we're going to end right now, but we're going to meet again, as I said before, at 5:55 in this very room. And we are going to announce our best paper and best poster and best demo awards. And then we'll have dinner in the next room. As far as the program for tomorrow goes, we will start at 8 a.m. with the breakfast, followed by our sessions, starting at 8:45. And then we have 3 sessions tomorrow, all paper presentations. We'll start off with session 5, which is wearable and cellular security, followed by session 6, which is authentication and protocols, and we'll end with session 7, which is wireless security. Obviously, there'll be a short break between the session 5 and session 6, and there'll be a lunch break after session 6. And we are probably going to be done by 3:45 tomorrow afternoon. So thank you very much again, everyone, for staying back, and I'll see you guys at 5:55 over here. We'll wait for a few more minutes for folks to trickle in, and we'll get started soon. Thank you, guys. Kavita? I think we can get started, Alexandra. All right. So, good evening, ladies and gentlemen. I hope you all have been enjoying the conference so far. This is the final, I would say, event of today, the award ceremony, and then obviously followed by the awards dinner. So without further ado, let me, call on Yongdae, Professor Yongdae Kim to, announce the Best Paper Award for WiSec.
As you know, always Best Paper Award has a lot of competitions, and it was actually very difficult to pick one. So I actually suggest steering committee to, instead of one, next year they have to choose two. But this year, actually, we had a committee of members, and they unanimously decide on one paper. And yeah, it was actually very strange because we asked everyone in the committee, which one, can you rank these 4 papers? And all 4 of them have the exactly 4 plus 2 and have the exactly same answer. And the best paper goes to AirGuard, protecting Android users from stalking attacks by Apple Find My Devices, which you just saw the presentation. Alexander Heinrich, Niklas Bittner, and Matthias Solik from Technical University of Darmstadt, Germany. He should have come earlier, but his flight was delayed and he missed the flight and he almost couldn't make it, but finally he's here. And
well, thanks a lot. I'm not sure what to say. Thank you.
Want to give a speech?
Okay, this is really cool. I don't know what to say. Thank you for it, but I think this is a recognition of that the work that we did actually helps people, and this is really cool. Then, and thanks. It was a great.
I think this represents how many hours he spent on reverse engineering the Find My devices.
All right, fantastic. Congratulations to all the authors of the Best Paper Award winners. Fantastic job as always. But obviously, as Professor Kim mentioned, we had a lot of competition, a lot of fabulous papers. Keep the papers coming. Hopefully, WiSec 2023 will have more papers, more competition, and more awards, as you mentioned. Right? Next category is the Best Poster Award, and that will be presented by Professor Eric Tews, who's also the Best Poster Chair. Best Poster Chair.
Hello, I am the Best Poster Chair. It's a pleasure to announce that we have a winner of our Best Poster Award. We had the poster and demo session yesterday evening. It was quite interesting. We had even 2 remote presenters, which was definitely not easy. And we had a lot of interesting stuff there, and I interviewed every one of the participants. One of the posters I spent a lot of time with, which also won the award, is passive drone localization using LTE signals. Congratulations, that was an interesting poster. Was a definitely interesting idea. I have also a small present for you. And yeah, would you like to say something about your poster? Because you were never on stage with your poster before.
I don't know how to say, but I'm presenting my for the another author, but yeah, I think it's interesting work, and I will improve it based on the comments received from you. So yes, that's all. Thank you.
Thank you. Congratulations to the Best Poster Awards winners. Thank you, Professor Tews, for also doing the needful. The last category is going to be the Best Demo Awards. I'm going to invite Professor Alexander Dmitrienko to come and kindly present the Best Demo.
All right, I guess I would like to tell a bit how this award was chosen. Unfortunately, I don't really know much about it. But yeah, so we have the winner, and I'm sure that the winner was the best demo which was presented here. And the winner is yeah. Adversarial metasurface in the middle attack. So great job. So well deserved. We are not supposed to shake hands. So would you like to say something?
Thank you very much for the award. It was just interesting to share this new project and fabrication technique that we have with all the people from very different backgrounds than ours. So we were very excited to see how people were excited about our work. So thank you very much.
Don't go yet. We have a few, I need to talk about a few other things, probably make it quick. Thank you, Alexandra, for doing the needful. And again, congratulations to the Best Demo Awards winner as well. Obviously, no conference is successful without volunteers who do a lot of hard work. And so we wanted to just spend a few minutes recognizing the hard work of everyone who was involved in organizing this. Let me begin with our program co-chairs for basically, obviously, organizing the program, doing all the reviews, making the schedule. So let me start by calling Alexandra for showing our gratitude for all the hard work. Thank you very much, Alexandra. Youngdae, he was our program co-chair as well. Thank you very much for all the hard work, making this a success. Obviously, we had a lot of behind the scenes, and I say behind the scenes because really truly they were behind the scenes, but a lot of times all the other volunteers and organization committee members, and I'm going to call everyone. Please come forward and just accept our I would say minor certificate or token of appreciation. Let me start by calling Anindya, who served as our publicity chair and sent out all the beautiful tweets that you saw, and publicizing WiSec 2022. Thank you very much, Anindya. Obviously, one of the most difficult challenges of this workshop was the video recording and the live streaming. And I don't know if you noticed this, but we have been live streaming this conference for the past 2 days. And the significant force behind it is our poster co-chair, Eric. So there was no title for really the AV expert, but he's also the poster co-chair. So he's done a lot of work. So I really want you to give a really big round of applause to Eric. Eric, please. Eric. Thank you so much.
Thanks a lot.
For your service to WiSec. Thank you. Is Yanmin around? I saw her in the morning. Maybe not. Sashank, Hina, Rocky. Okay, so then I call on another tireless volunteer who's done so much. Again, not only in the last couple of days, but ever since we actually received the WiSec 2022 from the steering committee. And he's actually our web chair, and he's had so many different hats. He's been a web chair, he's been helping out with the AV stuff, he's been lugging around stuff, doing everything I asked for. So Raveen, thank you very much. Please come forward and accept our gratitude. Thank you. He is, yeah, he is. So I obviously there are a lot of people who are missing in the crowd right now, but I want to also appreciate the work of our other poster co-chair, Shishir, who couldn't travel over here, Yanmin, who was our registration chair, who tirelessly helped to set up the registration website, and obviously there were many questions from many of you about registration, so she answered a lot of them. Our local organization chair, Hina, again, who's not over here, and she helped me organize this beautiful venue with a lot of good food during the conference. Rocky and Ning, who served as the travel grants chair, and many of you are students and you have received travel grants, and they're the ones who were really significant in kind of arranging that. And finally, obviously, Amjad, who's also not over here today, at least in this setting. He was also the web chair. Lastly, I also want to really thank all our student volunteers. Kavita, Nisha, they spend tireless days, past couple of days, sitting behind the registration desk, making sure that everyone gets checked in, giving them the right information. And direction. So, thank you very much, guys. Let's give a round of applause to them. And that kind of, brings us to the end. I want to kind of just give a shout out to our sponsors. Obviously, our technical sponsors, ACM and ACM WiSec, who actually made this event possible, or who actually making this event possible for the last 15 years. We had good corporate support this time. We have TII as our gold sponsor from Abu Dhabi. Thank you to them. Google as our silver sponsor. Thanks to them as well. UTSA Matrix AI Consortium, who was the Best Paper Award sponsor. Thanks to them as well. And NSF and ACM WiSec for funding all the travel grants that we were able to give out to all the students. So again, I thank the sponsors. So I think with that, I conclude this award ceremony. I hope you guys are hungry. We have a lot of food. So we basically, in the same setting, we grab food, and then there is a nicely decorated banquet room next door, and we go there and we enjoy our meal. Thank you very much.
Let me just say one thing. I mean, among all of us, I think who did the most of the work was Matija. So let's thank Matija. And dinner time.